Hey guys, welcome to another installment of Ferris Makes Emulators. This time we are going to be continuing our N64 emulator that we started in the last episode. If you haven't seen that, I should probably link that like now. One second, let me pull up a link to that. Basically, last time we just sort of basically started the project and we started getting to the point where we were going to make the machine boot. Or we're going to actually try to run some boot code by emulating the CPU. We basically spent a lot of time figuring out how to disassemble this and what kind of tools to use, and just setting up the basics of the project, and just only barely started to actually model the CPU. Fairly long process, but we got there in the end thanks to some help from some awesome people in the chat, TJS90241 specifically, and a couple other guys. So thanks to them, shout outs to them. That was really awesome. And yeah, so we'll be continuing from there. Here's the link to the last episode. And yeah, pretty cool stuff. So before we actually dive into sort of where we left off, I did, after like recording the video and putting it up on YouTube, I passed it around on Reddit and a couple other places. And one thing that totally happened is that a lot of people gave me a lot of really good feedback on like, hey, you should use this tool for this or this thing. So I want to kind of go over some of that feedback before we begin. The first thing I actually want to do is actually, let's go over, yeah. So one of the things we were doing is we were looking at the code for the boot ROM. And we got to the point where we could see, these first few instructions. But it was a really slow process because the hex editor that I was using was really slow, and it was really annoying to copy the bytes. So the first sort of tool that I wanted to show that we'll be using more now is called HexFiend. And HexFiend is just literally a hex editor for Mac. And it's pretty great because in this case I have the boot code here, and I can just select a huge string of this, copy, paste it into our online disassembler, and magic happens. Except the online disassembler doesn't seem to handle state very well. So I got to go swap back to little endy and then back to big. But once you read it, this is big endy, and then we actually have some boot code, and we're looking pretty good. So that was the first thing. Thanks to Daniel Collin for that on Twitter. He's also known as Emoon of TBL, if you're a demo scene person like I am. Pretty cool guy. So that was pretty cool, and I wanted to show that off. So we'll be using that if we ever need to look at some bytes some more. Let me look at my notes here. Another thing is that one of the things that I find really annoying is navigating documentation. Another thing that Daniel pointed out to me was a tool called Dash. Dash is literally an app for navigating documentation. I believe it's only for OS X. But the thing is, like, you can get the standard Apple documentation here, but you can also load custom documentation packs. So in this case, I have Rust, and so like when we were looking for env-args in the last one, I can just type here args, and I can select which one of those. I can add a space and also start like searching within that file as well. So we'll be a lot faster when we're looking through that. So thanks, Daniel, for that. Another one that he showed me was called Console Calc, and I thought I installed it, but I guess I didn't. But anyway, it's called Console Calc. I recommend that you check this out. The Lox Dash is the best. Yeah, it is really, really good. I'm absolutely advocating this. So this is pretty great. Yeah, one more thing. Sorry, I still don't really know how I'm going to be recording the chat, so we're going to have to miss that in this recording. But I'll figure that out before the next one, probably. The Lox says there is a Linux clone, so good to know. For those of you on Linux, good thing to have. So really cool stuff. There were a couple other things I think I wanted to go over. Nope, that was the tools. And let me look at my notes. Yeah, so another thing is that if you guys wanted to sort of follow along, it might be really difficult for you to obtain a ROM of your favorite game. So I pulled up a another test ROM that we're going to try using. Again, if you're familiar with the demo scene, it's this like sort of underground community of people who basically make real-time demonstrations on mostly old hardware, but also new hardware as well. Basically, these are just like effect shows. Like, it's not a playable demo in the sense that you can play it, but it is like, hey, look what I can make this console do. And in particular, I'm going to be using this MGC 2011 demo by a group called Retroactive. So I'm going to post this link in the chat here. So that'll be coming in a few seconds. And this will be really cool because this is a homebrew ROM, and now we can actually rip it apart. It's public domain. We're allowed to have this. So really cool stuff. TJS 90241 is about to say something. No current emulator runs that ROM. And I actually saw that coming because I read in the README that it did require some weird timing stuff and all this other thing. But I don't know. It's at least a ROM that we could take a look at. Actually, TJS 90241, if you have a better one that you want to recommend, I'm totally willing to check that out. And it's not discouraging. It's actually quite helpful. So thanks for that. Yeah. So cool stuff. Just kind of reading the chat. But I think that was just about everything, unless I'm forgetting something. My notes say that I'm not forgetting anything. LAC's Fire demo should be pretty straightforward, frame buffer only. I'm actually going to look for that. Go back to Poet, which I'm sure you can get that on there. Probably prods. Oh, Orkmork gave us a little link for this. Codeslinger001, what was wrong with the Ocarina ROM? A couple things. First of all, it's kind of difficult to get legally. Another thing is that it does employ some copy protection where one of these homebrew ROMs might not. Fire demo better trying to find a link. I believe Borkmark did find one. Let me click that link. Oh, he gave a link to just N64 homebrew stuff. Cool. So here's I guess tons of stuff that we can download and try. Let's see if we can find the Fire demo in here. Fire demo by LAC, PD, and Nintendo 64 ROMs. This is not a site that I'm advocating, but I do know that we are allowed to have this ROM. Go ahead and find that. Show us lots of fun ads. Fun times, fun times. All right, looks like we got it. Zagamik Harvest, risky click of the day, indeed. Indeed. Okay, cool. So we got another ROM here. Fire demo by LAC. Hopefully someone can find a better link that I can actually feel more comfortable distributing to people. But at least we know that we can use this ROM and take a look at it, so that'll be really cool. Awesome stuff. So I guess we should sort of get into it. Oh yeah, that was the other thing that I was forgetting. Codeslinger001, time for uBlock. Don't know what uBlock is, you should totally fill me in. Yeah, so someone, X13 Pixels is so amazing, thanks so much. Thank you so much for watching. I think you're amazing. So this project, amazingly, for me, got 51 stars already, and I'm so excited about that, you guys. I'm really happy that so many people are tuning into this and really interested in this project. It means a lot. I really thank you so much. In particular, though, one guy did a pull request, and a couple guys on Reddit also pointed this out. So if we look back at the code, let me just open this here. We didn't get that far, so there's not that much code. In particular, here. So in this case, we have this CPU structure here, and it just has a bunch of the registers on it. That's all it is right now. Apparently, uBlock is a lightweight ad blocker that's still good. I'll have to check that out. Thanks, guys. Then we implement it, and we set all these things to zeros, except for this Boolean, which is false. And then later, we also have the CPU struct with all these different fields. And we also set all the values on that to 0 when we create it. And the thing to note here is that basically what we're doing is we're just kind of zeroing out the whole struct. We're just setting it all to default values. And in this pull request, and also in some of the other things that those guys were mentioning, this guy was wondering if there was a way better way to initialize all these values just to like defaults. So he checked it out, and there is one in Rust. So Rust has something called traits, and you can, when you use traits, you can kind of think of them like interfaces in Java or C#, but really they're more like templates in C++, where they're kind of expanded compile time, and got a lot of cool benefits. But the point is that they're used for better abstraction, and they can do a lot of things. In this case, we have a trait called default, and default, what you can do on structs in Rust is you can have it derive specific traits. I don't think I've actually used that in the code yet, but I definitely probably will later. We're probably going to derive debug on our CPU struct, and that will give us like a default implementation of like how to print the struct, which is going to be really helpful moving forward. And in this case, they have this sum option struct derive default. What that means is that instead of doing excuse me, the struct name : new to create the struct, you can actually do default : default like this. And what that does is, because you derived from the default trait here, this will actually get an implementation of the default function, which will zero out all the values or turn them all to zeros. And then this, of course, goes into more detail in the Rust documentation about like, oh, what if your struct also had a different struct that didn't have default on it? Well, then you get a compiler error, all that kind of fun stuff. But anyway, in this, I believe this was Zorend did this pull request. So what he did is he actually went and if we look at this, he just went ahead and derived default on our CPU struct, had function new return defaults. I may actually change that, but we'll see. And he did the same thing for CP0. MoveAway00 says, you also could do struct name : default. Yes, you can, because the struct itself would have that method, so you would, or function, so you would actually be able to call it directly if you wanted to. Up to personal preference. So yeah, so what he did here is do this for us, and so I'm totally going to accept this pull request. So that was pretty cool that we got that. And I just thought it'd be cool to do that live on stream. So I'm going to go ahead and merge that. Lovely. So now I'm just going to pull that back down. And there we go. Now we have a lot less code that does exactly the same stuff. So pretty cool. And I'm pretty sure this still doesn't run. Oh, it does actually run. Okay, cool. Fancy, fancy. A lot of unused stuff, but that's okay. And I know my font is ridiculously large. That's so you guys can hopefully read it. I may actually make that a bit smaller if we end up keep having these warnings and stuff, but we'll get there. So cool. So I believe where we left off is I was looking at these CP0 registers, and we were starting to implement the startup state for the CPU. So when you power on the machine, like excuse me, if you power on the machine, a bunch of registers will get default values. And I was going to start modeling these. And initially, I just made all of these registers on the CP0 unsigned 64-bit values, right? And then as we were looking at, how big some of these registers actually were internally, I think it was the config register, if I remember correctly. I can pull up that document as well. I think think it was here. Yeah, it was saying certain bits of the config register are set to certain values. So we went and we looked at the config register. Where was that? Have to find it in here. But anyway, the register itself was only like 20 bits long or something. And so instead of modeling it as an unsigned 64-bit value, I think what I'm going to end up doing is we're going to abstract the interface for reading and writing these registers, so you don't access these directly and set them to values from outside this structure. Instead, what you'll do is you'll say like TJS is chapter 5 or 6, if I recall correctly. Thank you. That will help us find that. Yep. Looks like you're right. Config register. Bingo. Yeah, so this whole thing is, I guess, 32 bits wide, it looks like. So anyway, much smaller. And what I want to do is I want to semantically model each set of these bits. So instead of like storing the config as a 64-bit value inside the struct, I'm going to store it as a collection of like, oh, there was this part which was an enum that could be 1 or 3 values or whatever. Code Slinger 001, it looked like a lot of them were 32-bit. Yeah, I'm guessing a lot of them are going to have to be modeled differently than 64-bit. I made them 64-bit initially just because of what JRRA1 is saying, which is that you can access them as 64-bit via the DTMC0 or DMFC0 instructions. But yeah, I think we need to model this a little more ergonomically than, yeah. A little more semantically accurately, I think I would say. You could argue that keeping them as 64-bit values is going to be an optimization, and then we should keep that for speed, but I think that that's going to be okay. Not too concerned about that right now. I probably should be later, but I'm not right now. So yeah, so what I'm actually going to do is I want to actually erase all of this. Because again, I think we should model each of these one by one, and until we know what they do, I don't think it's worth having them around. So we'll erase those. These will stay the same. So that's pretty cool. So config register. We have like these EC bits. I guess these are, not entirely sure what these are. A lot of this is going to be me reading data sheets out loud, hopefully. Also, I guess this font is extremely small. Let's see if I can zoom in a bit. I don't know if that helps at all, but hopefully it does. Yell at me if it doesn't. EP and BE areas are initialized on cold reset. These areas can be read or written by software. Default values are as follows: EP and BE. Okay, so EC is the operating frequency ratio. It's read only. Value displayed corresponds to the frequency ratio set by the div mode pins on power application. So what this probably means is that there's like a clock multiplier, a clock divider. Because I believe when we saw the block diagram of the CPU, it had its own internal clock generator. And I believe that these div mode pins are probably used to select what speed of a clock that will actually generate. And that would make sense that then this part of this register would basically show what that is. And then, of course, EP is the transfer data pattern. Or is that part of this? I guess that's something else. I don't know what that means. 2 double word 6 cycles. I guess this will... This might have to deal with like how reads and writes occur on the bus. Something that may actually not be that important to us while we're doing high-level emulation. I guess we'll find out later. BE is whether or not you're going to be reading out memory either in big endian or little endian. And it looks like you can, if we remember from last time, we read this note that register can only be changed or You know what I bet this is actually? I bet this is when you're reading and writing words of memory in, and that's why you need some no-ops between when you do that and when you read or write. I wonder if that's either to flush the cache. Probably not, because cache is quite large, but I guess we'll see. But anyway, the first things that we're going to want to do is model the parts that are going to be set up on startup, and I think we'll just model the rest of these states sort of as we need to, and just kind of ignore them for now, just to sort of get a move on. Because I really want to start executing this boot ROM code sort of as soon as possible. So let's get into that. Again, the EP and BE areas. Transfer data pattern. The EP is 4 bits, and I'm actually wondering why that is. But these are, see, so this register here is 4 bits wide, but there's only like 3 like logical values. And Rusty Bicycle, I don't think you can have an empty struct gate, so you'll need at least one. That is correct. That is true. You can make what were they called? Unit-like structs, I think they're called, and you do something like that. I can't remember the syntax for that. But then you've just created a unit value, not really an actual struct that stores data. So that's the difference. But I actually want to look at this CP, this EP thing here. We're going to make another struct for that. I'll actually do an enum for that. Enum, not really sure what to call this yet. We'll call this CodeSlinger001. What is RFU? I have no idea yet. I guess we'll figure that out together. Enum config. That's not what I want to call that. Config EP. I'll write a little note to do better name. If we do a couple more of these, maybe the name will become apparent. FPGA Nuga says reserved for future use, hardware term. Good to know. Thank you. Move away 00. Empty structs with curly braces became okay in Rust 1.6, maybe 1.5 or 1.7. That's definitely why I didn't know that, because I remember having issues about that in probably 1.3. So good to know. Again, guys, I'm still kind of getting over the cold, so if I'm coughing or snorting or being gross in general, just I apologize. Yeah, so we have let's just do this as D, DXX, DXX. Again, I think these could probably be named better, but they do match what is written in the data sheet, so I kind of like that. And then we'll just do RFU. And in this case, CodeSlinger reg config EP. I'll actually call it that, reg config EP. In Rust, it's customary for type names to do camel case like this, and then it's customary for variable names. So we'll do reg config EP is a reg config EP. See what I mean? So like the member or the variable will be snake case, and then the type will be camel case like this. So thanks for the suggestion. That looks good enough for me. So then on the power on resets, we're going to set the self.reg config EP is reg config EPD. And there we go. So now we've modeled that part of that register. Next thing we're going to do is, so it was EP and BE areas, and that was the EP area. And there's the BE area, which is the big Indian whatever. I'm still going to leave this to do better name, because we might end up with something more descriptive. But for now, that's definitely the best we got. And this should only just have 2 values. I bet this is 1 bit wide. Yeah, right here, 1 bit. Reg, we'll follow the same naming convention. Reg config BE like BE probably stands for Big Endian in this case, so we'll probably be able to name that better. But again, I'll wait till we do a couple more of these and just get more used to reading this particular datasheet and the terms associated with this processor before we start making those changes. At least that makes me more comfortable. Yeah, so this value was either little endian or big endian. And by default, it looks like it was 0. Nope, it was 1, big endian. Good to know. Also, that was helpful of them to, when it writes these values for the startup state, it's writing them in bits in binary representation. Move away. Deriving default will mean the default is little endian. That is correct. We will override that in a second. Good call. Or actually no, because we're okay, because we decided in the last one that we would, for just when you call new, you'll just get whatever the default is, like a 0.struct, and then you're expected to call power on reset after you've created the object. And again, I said this in the last one, I don't typically like to do things that way when I write libraries, but in this case, I feel like it more accurately represents the hardware. Like, if you just get a brand new piece of silicon, you would have been expected to follow the power on procedure before it actually acts properly. We can, of course, change that later, but for now, we'll leave that as is and then fix it here. So then we had the reg config be. And oops, reg config be, and that was going to be beginning. Cool beans. So where was our main down here? View.power on reset. And what I'm going to do here is I'm going to just print the CPU. So println is print line. This creates a hole where that's going to be printed in. And then we do CPU, do a little reference to that. So it doesn't own it. And we'll just debug print it, which means we'll also need to derive debug on all these structs. No problem. So again, what I'm doing with this derive syntax, if you're unfamiliar with Rust, is I'm just saying that, hey, when you make the struct compiler, also give it a default debug implementation. And when it implements debug, that basically adds I believe it's a debug format function, I think it's called, that gets applied to the object. And then, it gets added to the object. And then when you call println with this particular kind of format here, with this colon question mark here, then that will use the debug implementation. Default cannot be derived for enums, only structs. So I guess we have to implement that explicitly for enums. Didn't know that. Now I do. Let me actually pull up dash. Oops, in the wrong documentation, I think. Yep, and here we have an example of how to do it yourself. CodeSlinger001, are those Cherry MX Blue switches? I think they're actually MX Browns. Might be reds, can't remember. Apologize for the loudness of the keyboard, but I do have, I could switch to a quieter one, but I'd much rather use this one because it's a lot better for my wrists. For production code, would you get rid of the debug derivation? It doesn't really hurt to have it, because the thing is that if there's a couple different traits for printing. One of them is debug and the other one is display. And display is like if consumers of your library wanted to print this, and so if you didn't have this colon question mark and you just did this, it would do the display implementation. And that's usually meant for like, hey, we're going to show this to a user, right? Whereas this means we're going to use this for debugging. And sometimes it's useful, even when in production library code, to have that implementation available for people who are consuming a library to be able to also debug with it. So that's pretty nice. Chemical Nova says -- release builds will optimize the debug away. I actually didn't know that. Might have to double check on that. And Rusty Bicycle, what would be the purpose of defaults on an enum? Good question. I guess you could think of it like it might give you the first value, but I mean, when you really think about it, Rust is really heavy on semantics, and I guess it wouldn't, it could be either one. So probably doesn't make a lot of sense to have default here. I was just trying to type less. But no problem. All we have to do is impl defaults for reg config be. Ernest, so is this derived directive similar to the Haskell one? Yes, totally. Chemical Nova, it may, I believe it read it somewhere in the Restlang internals mailing list. So maybe release compiles that out. Might have to test that. We're not sure. But either way, I think in production code I would leave those in actually, because again, a consumer of the library might want to debug a specific struct, and you should let them do that. In general, like one of the reasons why you do the debug with this and then display with this is that again, like display is meant for like let's pretty print this so that our users can see this data. Debug means let's print this on the terminal so I can see what I'm doing as I'm debugging my code. So semantic difference there. Yeah, so then this will have, I believe, go ahead and move that over there. Oops, wrong arrow. Function defaults, which will return a reg config be, and that will return reg config be : big endian. Here, since we have to implement the default, we'll just do the right one. And we'll do the same thing for reg default or reg config EP. Ernest, isn't it awesome to see that kind of stuff in a systems level language? That gets me excited. Function defaults. D, I believe it was. Another thing about Rust is like in C or C++, you would have to type return this. In this case, this is an expression-based language, so you'll just type the expression, and the last expression in a scope ends up being the value of the scope when it's evaluated. So good stuff. All right, let's try to run that. Yeah, so not panics because in our main function, we're still loading here. We're still loading the PIF ROM, which is our boot ROM, and then the ROM itself. And of course, I didn't specify either of those on the command line, so I need to do that. On my disk, it's going to be, I believe, ROMs N64 pifdata.bin is our PIF ROM, which is our boot ROM, and then we'll do ROMs N64. Where was that fire demo? Where did I put that? Fire demo. There we go. So if we run that, it doesn't crash, and as you can see, it printed our CPU. I believe there's a way to make this print pretty, and I think it's to replace this with a hash. I was incorrect. So let me go ahead and look that up in some of my other code. I definitely used this like 2 days ago. This little piece of code I'm pulling up is you put a hash between here. It's a compiler for an old language called Blitz Basic, which I used to use when I was younger. And I found some code written in that language that I wrote when I was like 13. I wanted to run it. I couldn't find a compiler for OS X, so I'm throwing one together. The project's called Butterball. It's on my GitHub if you want to check that out. Yeah, move away 00, add hash, not replace. Unfortunately, because of the chat delay, I had to go look it up. That's all right. Thanks for the help. Cool, so now all we've done is we've created the CPU and we called power on reset on it, and then we printed it. And what we get here is exactly what we asked for. There's a struct, which is CPU. Then we have all these registers here. These are the general purpose registers here. Then there was also the floating point registers here. Then we had our program counter. Then these other registers that I don't quite understand yet, so can't remember what they do. And then here was our CP0, the different parts of the config register. In fact, actually, If we wanted to be cheeky, we could also make this config register its own struct just to sort of split it up even more. And I actually kind of like that. So I think I'm going to do that. I'll do it here. And we're going to derive default for that. And debug as well, so that we can print it, see what we're doing. And that will be struct config reg. Or reg config. To match our other ones. Something buzzed. Oh, not important. And then this will have these components here. So let's just move those up there. And we're going to move some other stuff as well. This will have a reg config, which is going to be a reg config. Fancy. Yeah, we're going to do an impl for this. And function new, which will give us the reg config. Actually, I think I'm going to erase these new functions that just return the default, because I think the more common way to use these is just to call the default function. And consumers of this library won't be too confused by that, because they'll call new and they'll see it doesn't exist, but then they'll see it gets default, so it'll be okay. So I think we'll just do that. But we do want to implement power on reset on this. And actually, we'll copy this. And this becomes reg config.power on reset. And this becomes that. And happy times. Yeah, and I'll delete you up here. And then down here, where we actually create the CPU, I will call defaults. Run this, we should get the same thing. Unresolved name reg config. Did you mean self reg config? I sure did. Self. There we go. And yeah, we get the same thing. So cool. So now we've actually started to model our CPU, which means we're actually really close to being able to start looking at instructions, which is pretty rad. I'm pretty happy about this. I wanted to get to running some kind of code today. It looks like we'll be doing that. All right. As for the rest of the config register, I think we'll wait until we need to deal with that to implement it. I think now actually is a good time though to start splitting this up into different files, because it's getting a bit messy already. So I'm going to first just take all of this. And dump it in a CPU module. So we'll do cpu.rs. And I don't think I'll split it up further yet. But we could also split that up into multiple file module with the different registers and different files. And at some point, I think that gets to be a bit much. We'll see. So we'll declare that module, mod CPU. And we'll just put CPU : here. And default is inaccessible. It needs to be public. Interesting. I wonder if that's because, yeah, because it was the struct was private. So we just put pub in front of this. I don't think we have to make anything else public, and we don't want to make anything else public. Power on reset is private. That is correct. So make that public. And all this is doing is just making sure that these names are visible outside of this module, so that our code up here in our main function can actually call that. And that should be it. There we go. Awesome. And a little nicety there is that now all these other structures in here are inaccessible to the outside world. Only the CPU, which is going to use them, actually sees them. That's pretty nice. Same with this num_gpr thing here, which is only going to matter internally in this CPU. So that's pretty cool. Nice stuff. I'll do a little commit. I got asked about this last time. My editor setup is just Emacs, and this Git client is called Magit, M-A-G-I-T. Type that in the chat. and it's really, really good. But it's, I mean, I think Vim also has a built-in editor for doing this. But yeah, so I'm just staging everything, then I'll commit. More CPU modeling. In general, when you do these projects, or at least when I do a lot of projects, my commit messages aren't as good in the start as they are later, because we just kind of want to get the ball rolling. And I like to commit a lot, at least in the early stage. Push that. And we should be good to go. Cool. So now what we want to do is actually get the CPU running. And the easiest way to do that is just to, we'll create a function called cpu.run. Just going to call it already because I know that's what it's going to be called. And this will just run it indefinitely. Now, of course, we're going to have to do some other things with that, like make that process interruptible to shut it down properly and lots of other stuff. But for now, I just want to run as many opcodes as we can in the loop. And when we find one we don't understand, we'll just panic, which is Rust's way of like throwing an exception, basically. All right, Rust guys will be like, no, it's not exceptions, and you're right. There are a lot of subtleties to that, but for all intents and purposes, it's a way of killing a thread because of an unrecoverable error. So what we're going to do is implement that run function. Doesn't it need to take some code to run from CodeSlinger 001? Yes, it does, and that's going to. This function was going to lead me into that next point, which was we're also going to start emulating the next thing we need, which is the actual like memory mapping unit and the actual memory mapping. Dopeman64, where is Mario Kart? Man, that'll be a while. Broken Mario Kart will be sooner. Pub function run. To-do different interface. This code's gonna be littered with to-dos. It's gonna be okay. To-do. So yeah. What we're probably going to do here is now, because we don't just have the CPU, we're going to actually have the whole system. And so that's probably where I start splitting this up more. Let's go ahead and make another module here. I'm just kind of thinking what to call it. It's going to be the whole emulator itself. I might just call it N64 for now. Let's go ahead and do that. N64.rs. And we'll go ahead and declare that module as well. We'll also change the name of CPU to MIPS 4300 eventually. JRA1, have you thought about how you'll handle memory? And CodeSlinger, would you model RAM explicitly? I guess that's the same question. So RAM is just going to be an array of bytes probably. And then we're going to have like a read word and write word to it. Might be array of words for speed again later. But again, if we just make a really simple interface where we're just going to read and write words, then we'll be able to change that and make it faster, slower. But I do want it to be its own like little array somewhere, and then the memory mapping unit is going to decide whether or not that's the data whether or not that's what we're going to be interacting with on the bus. Cool. So this is going to use super CPU. It is a super CPU. And let's go ahead and make our N64 struct. Oops, capital N. Oops. Rust compiler is really good at warning us if these aren't like capitalized in a nice way, so that's good. Borkmork, so are you going to ignore cache like virtually all other emulators? At first I am, yes. I mean, clearly it's more correct if we don't do that, but I think for the case of for the sake of getting stuff running earlier, I think we'll just deal with that later. That's going to be part of the CPU anyway, so I think we'll be able to handle that later. Uncle Karl Marx, how much unsafe do you foresee in the memory model? None. So far, I don't think we'll use any. it would probably be faster to just use pointers and do actual, host CPU word reads and writes. But we're not going to do that, at least not yet. That's optimizations for later. So the N64 is going to have a CPU. So nice when I get to write it like that. And that'll be pub. We're going to implement stuff on the N64. And yeah. Get my caffeine on. Much better. Yeah, so pub function new. I know it needs to be public because we're going to access it from in here. And all we're going to do is return, that needs a return value. Oops. TJS 90241, what is your favorite programming beverage? It's actually totally Dr. Pepper. I have Coke right now because I do, but it's Dr. Pepper, absolutely. The intellectual drink made for the chosen, if any of you have ever seen Sidesgate. So this will return an N64, where the CPU is going to be CPU default. And Rusty Bicycle, Budweiser with a side of Jameson, good choice. Don't man 64, Mr. Pibb. I have to disagree, sir. Yeah, that'll do. Codesinger 001, no default trait for N64. Yeah, let's do that. Good call. Oops, derive. And we'll use debug as well. Or actually, I won't do that until we need it. And that should be it then. Cool. Ryan Hebert, water, no guilt, second place, Dr. Pepper. I got both. I need my hydration, I need my caffeine. And unfortunately, they're always packaged in separate units. Yeah, so now instead of creating a CPU here, we'll do let mute N64. So it always feels so cool. N64 default. We'll do N64.poweronReset. And we'll run the N64. So pretty, so pretty. It's only pretty because we haven't gotten to the hard stuff yet. So yeah, so we'll impl N64. You know the flavoring in Dr. Pepper is prune juice, right? And it's amazing prune juice. Prune juice and bubbles and caffeine, that's what I like to drink. Pub fun power on reset. And we'll call CPU.power on reset. And of course I forgot my mutable self reference and self dot. And whoops, there. Use of undeclared name CPU, yep, because that was going to be CPU. No method run found, that is correct. Pub fun run. Ryan Hebert, so cool you said my name right. That's either sarcasm or it's Hybert, or people usually call you Hybert. I lived in Norway for many years, so I got the Germanic IEEI thing going for me. Pub fun run. Right now we'll just call self.cpu.run. Self is not available. That's correct because we need and mute self. Lots of little syntactic mistakes I'm going to make, and that's going to be okay. No method name run on CPU. Yep, because I don't think we ever added that. So let's go ahead and open the CPU. Oh, we did now, did we? Yeah, because this ended up being static because we also forgot env itself. Unmasked Games. Dude, I didn't know you streamed. I was expecting games. This is Ryan Maskell. Ryan Maskell. So good to hear from you. He's a kid who went to my high school. Pretty awesome guy. Yeah, so I'm building an emulator. Codeslinger001, Uncle Karl Marx. Man, this compiler misses nothing. Rusty is love. Totally agree. I love this compiler. Ryan Hebert, no sarcasm. Everyone says it wrong. It's actually German. Definitely believe that. Cool. Running stuff. Running consecutively, it doesn't compile anymore, so we're not getting these warnings. I love some of these warnings, by the way, like unused variable PIF. We can turn those off, but I want to keep them on. If you want to actually override these warnings, what you can do is you can prepend the names of the things that it's warning you about, but with an underscore, and that will make that linter ignore that. And sometimes you'll want to do that because you'll want a name in there for code clarity, even though you never use the value. I believe I did that in a parser once or something. Like, don't do it too often, or I don't do it too often, but happens. MS Games is way more badass than what I do. Man, what you do is pretty sick, though. Or at least what you did last time I checked with you. You were doing like web design stuff out of Coeur d'Alene. I don't remember. What are you doing these days? So, yeah. So not only do we need the N64, we're going to need sort of, yeah. So we have, let me think a little bit. MS Games, yeah, design and web, good. Glad you're still doing that. You were good at that. Yeah. So what I'm thinking is that the CPU, because it needs to read and write stuff, it needs to know about the memory. So you're going to have a reference from the CPU object to some kind of memory object. Now, before when I've done emulators, I've made I have this N64 struct here, and I've made that like the whole system. So you would read and write bytes to the N64. So like this object was the system bus. Not only is that not very elegant in general, as I found out later, it's also kind of difficult to do in Rust. Like if you have, because what you'll end up with two objects: the N64, which owns the CPU, so it has a reference that way, and the CPU, which talks to the N64. So you have this circular reference. Rust does not like circular references. Rust, because it does automatic memory management, it likes to have if you're gonna have mutable objects and you use the normal references and you don't, I mean, it does have some things for internal mutability, but I'll get to that later. It doesn't like circular references because it wants everything that's going to be mutable to have one clear owner. So like the thing is that when you have Codeslinger001 DAG, I don't recall what that means. One of those terms I definitely know I need to know. Oh yeah, DAG, direct acyclical graph, of course. Yeah, it likes DAGs because then you always have like one owner, and it likes immutable data as well. But if you're going to have something mutable, then you only want one thing to be able to mutate that at any given time. And if you ended up with circular references of two mutable objects, that could be a problem for not only threading. There are also cases where threading is the obvious place where you might have problems because you might have two threads manipulating those things if your two aliases are from different threads. The other problem though is that Rust has pattern matching, and it's possible that you could match on a pattern and then go mutate something in that match arm, and then that mutation would actually make that whole match arm invalid because some of the assumptions that you make in that match arm maybe aren't true for the rest of the arm. And you can't do that if you have one mutable reference at a time. So it saves you from a lot of these kind of issues. This is all part of Rust's whole memory safety thing, and it's really awesome. It's really nice to have. But you do have to think a little bit more about how your objects are structured if you're doing object-oriented programming. And we sort of are in this case. Moveaway 00 and the classic iterator of validation is another example. That's another example of a single-threaded case where mutability causes problems, or where multiple aliases to something mutable causes problems. Yeah. Cool. So let's go ahead and look at the memory now, I guess. Yeah. So we're gonna have the N64 owns the CPU, and I think the CPU is going to end up owning the interconnection stuff just because of the way the mutability graph, or the way the mutability and ownership stuff will work. And then the interconnect will own the RAM. Yeah, I think that's pretty typical for people doing emulators in Rust. So let's start modeling that stuff. If some of this sounds unclear to you, it's probably me explaining it somewhat poorly. But when I express it in code, it'll start to make sense, I think. Let's actually, we'll do interconnect.rs. And interconnect is what will be used to model, all the buses on the system. Also, we need to go into, no, I'll do that later. Yeah, so pub structs interconnects. I believe I've seen this pattern used in the PC Walton is the guy's name. The NES emulator. It's a really well-known Rust project. I can't remember what it's called off the sudden now, but it's a NES emulator for Rust. I believe I've also seen it in Game Boy emulator in Rust, and I believe the PlayStation emulator does it this way as well. CodeSlinger 001, this is going to beat up your cache. If you're referring to me having a bunch of different nested objects and you're worried about all the pointer interaction as we're doing all this stuff, then you're probably right. That might just totally destroy the cache. And he's talking about memory cache on the host CPU, and that may. So we may end up changing this stuff for performance later, but I really want to model this sort of as nicely and as elegantly as we can first, and then we can optimize it later. But that is a valid point. So we're gonna have, I guess, some RAM, and I'm gonna make a constant for this. And I don't remember how much RAM this has. I believe it had, was it 4 and 8 megs? Actually, the text spec's open right here. Yeah, 4 megs upgradable to 8 megs. We're gonna worry about the expansion pack later and just make this 4 megs. For kilobytes, megabytes. Because I'm bad at math, and so this will be. So this was one of the interesting things though, because this is what I thought. One of the interesting things about the N64, I almost didn't remember this. I believe each cell in this 4 megabytes, each byte is 9 bits. Because I think each one had space for like parity or something like that. Trying to remember. CodeSlinger 01, yeah, it is a 9-bit bus, and I'm trying to remember why. You see all the websites I frequent. Oh, here's someone's paper or thesis or something about the Nintendo 64 architecture by Courtney Getman and Colin Reeser. Thank you guys for publishing this. FPGA Nugget says you don't need to be worried about the 9th bit. 9th bit is totally invisible to CPU. The rasterizer uses 9th bit for anti-aliasing coverage info. Today I learned. TJS says it's not invisible, but in ordinary circumstances you can't access it. Also, it's used for extra Z buffer bits. That would make sense. RCP has an internal 64-bit data bus and 8-bit E bus, which I've assumed to mean extended. So lots of information at once. I'm actually a bit confused at whether or not the CPU needs to worry about this. But I'm guessing if we just model it as... So the thing is that the memory needs to know that this is 9 bits. And so what I'm actually going to do, again, even before CodeSlinger 01 tells me again that this will ruin my cache, I'm going to make these U16s. Again, we can pack this better later, but it's going to be a lot more ergonomic for us to code with if we just make them U16s. And then we'll do RAM size. And that way we've modeled the fact that there's a 9th bit there, but the CPU won't have to worry about that. TJS 90241, normally the MI MIPS interface will only interface with the 64-bit bus. Good to know. You can turn on eBus test mode in one of the registers and it will use the 8-bit bus. But nobody does that. Thanks, TJS, for the info. Yeah. So that'll be our RAM. We can also do derive default for this. So we'll just zero all this out, which is pretty nice. Don't have to write that. So we'll have a CPU, and we'll have an interconnect. We'll actually probably have to remove default for this because the CPU is going to need to have this interconnect available. JRI1 in the chat is asking if he is a VR4300 MIPS CPU, how do I flip that 9th bit? And I believe TJS will fill us in. Because I don't know. He says, you don't see that 9th bit from the VR4300, you aren't even aware of it. Only the RCP knows about that bit and chooses to conditionally expose it from the MI and the RCP. Really good info. Thanks again, TJS. It's actually a fun little thing we had here. Kind of want to just scroll through this and see how deep this goes, because this might be very useful to us. Data transfer is a lot faster than CD. That's true. It was also a lot smaller. RCP. Definitely recognize these diagrams. Although I am not at liberty to say where I saw them. Yeah, VR4300 only has a 32-bit bus used for both address and data, and 5 bits or so that are used to drive the bus protocol. So what he's saying is that the CPU itself is only going to be able to see the memory through a 32-bit bus, which makes sense because that's the size of our instructions. And he's saying that there's going to be 5 or so other lines that are attached to that, and that's going to say like, oh, I'm writing a byte or I'm writing a word or that kind of thing. Most likely, there's also probably going to be a lot of like control lines and that kind of thing, like, hey, I'm using the bus or I'm not, that kind of stuff. Bus protocols are they can be arbitrarily complex. CodeSlinger 001, isn't it common to have a wider bus than the ISA requires? Also, move away is pointing out that Rust doesn't have type level integers. Straights are only defined for arrays to a constant like 32. I do believe that. Remember that, yeah. Sorry, I'm getting distracted by the interesting things that are coming up in the chat. I really wish I had been recording this. I'll try to read out the most important stuff aloud. But yeah, we're gonna have to change the way that I've described the RAM. That's probably true. TJS is speculating a lot on how you might access those other bits from the CPU. JRA1 is adding this information to his stuff I don't want to do when I'm coding against the emulator list. Again, more diagrams I recognize, but I will not say where from. Texture cache. Figure limited, not geometry limited. If you don't know a lot of this stuff, that probably means you haven't done a lot of graphics programming. It's perfectly understandable. We won't have to deal with that till much later. Yeah. They did actually cite these sources. That's pretty funny. Okay, let's get a move on here. We're gonna have to change this. That'll be okay. But I just want to tie everything together first. It's gonna run the CPU. Yeah, I put the interconnect on here and then I took it off, and that's because the CPU is actually gonna have to own that. So we'll go back to the CPU. It's not my favorite thing that this ends up having to live here, but maybe we'll find a better way to do this later. I'm just gonna do that. And it's gonna be use super interconnects. CodeSlinger 001, shouldn't the CPU hang off the interconnect? It should in terms of like modeling the system nicely, but in terms of mutability, we want the CPU to own that. Yeah. CodeSlinger 1, that's where you'd put the RCP and RAM as well, right? Yes, that is where we're going to put the RCP and RAM, but that's because the CPU is the one that's going to drive most of that operation. Again, this is where probably some unsafe code is going to be used later. We'll figure that out when we get there. But for now, we'll make the CPU own the interconnect because the CPU is going to be the driver for the whole system. For now. Might change later. Probably will change later. But if we do it this way, then we play nice with Rust and we get all of our nice single alias mutable stuff. It'll be pretty cool. Yes. Losing my train of thought. Interesting discussions happening in the chat. Again, I will record those for the next episode. Yeah. So I believe we're done with that. CPU will have its default implementation. We're calling CPU. That we'll call CPU default. Interconnect will have its own default implementation, so we're good there. Read and writes will go to the interconnect. That'll be good. And yeah, so we'll go into main to make sure that we get our interconnect module defined or declared. Yeah, and we get core default not implemented for that particular. Oh yeah, we were also printing, implementing debug for now something that has this interconnect. That will not do. So we're gonna have to get rid of that. That'd have been fun to print all that RAM. I do think we'll be okay for the default stuff here, because we'll only ever be let me also clear when I do this. Oh, we just have that many errors. CPU cannot be formatted using this if it's defining a create definer bug. Manually implement it. What was that? CPU 0. Thought I removed that. Did I not save that? Did save that? We shouldn't be printing that anywhere now. Bug is not implemented for interconnect. That's true. Probably left it on the CPU. Yeah, there it is. Yeah, so we're gonna have to change how we showed this. How did I do this in my SNES APU emulator? Let's look at that. SNES APU source. Because I had some buffers and stuff in here in the APU, I think. Some IPL ROM for y'all. I'm just looking at some code. This was an emulator for the audio portion of the Super Nintendo that I wrote. Muwei actually says you just have to impl default yourself as the 4 megs, but I actually think that I might complain. I know one thing that's going to happen here is that we're going to need to box this at least. And then I'll just take Muwei's instruction of implementing default yourself. The reason we're going to need to box this is if we didn't, then that would mean this entire struct would live on the stack, and you don't want a 4 meg large struct living on your stack. Box is a heap owned pointer. So impl defaults for interconnects. Implement the default trait, and that's going to be function defaults. That may need to be pub. We'll find that out. I think you don't have to specify it because I don't remember. We'll see. Probably will tell me. And then we're going to say defaults. Oops. Default wall interconnect. And we're going to return an interconnect object. And that is going to say RAM is box new. And there may actually be issues with using box new here as well. And I'll go over those if that happens. It tends to happen on my machine. Don't end up having that much stack space. Yeah, so we'll create the array and just be 0 RAM size. It worked, but an unknown error occurred, and I'm more than willing to bet that that unknown error was that the stack exploded. So this is actually one of the things that is kind of annoying with Rust. Actually, let's see if we can just run it in release to ignore this problem, because I'll explain what's happening, but yeah, it works in release. So a lot of the times, at least on my machine, with debug builds in Rust, my stack isn't very large. And when you create an object like this, what happens here, if we look at the innermost expression here first, we're going to create an array that's filled with zeros. The type is going to be U16, so it's going to be all U16 zeros. And the size of that array is going to be, 4 million of those. Chemical Nova is telling me something about using a vector to heap allocate. There's also another thing that I'll go over, which is another solution to this. But yeah, the thing is that it will create this array, and it will do that on the stack by default if you just use this syntax here. So it will create this, 4 million, so I guess 8 meg array on the stack, and then it will create a box object, which will have space for this array, move that array into the box, and then it will remove it from the stack. So the whole stack frame for this function is going to be about 8 megs big, which is too big for my stack a lot of the time. Codeslinger 001 says 8 meg just happens to be the entire stack size on OS X. So makes sense that's why it also got an unknown error instead of knowing that the stack blew up. So there's a couple ways to fix this. One of these is to, instead of using an array here, we can use a vector. Vector of U16s. And that's what I don't like about that is that if we make it a vector, we've kind of modeled that this RAM is able to be resized and reallocated. The better solution is we can leave it as is, and we can use this thing called box syntax, which looks like this. Yeah, move away 00 just said that. And what this will do is it will heap allocate this. So it won't create on the stack and then move it into the box with that box new call. It will create a box with this much space already allocated on the heap, and then just create this there. Unfortunately, the box syntax is, because Rust is still in its early stages, the box syntax is unstable. So if we use box there, then we would only ever be able to run this on nightly. Now I have nightly Rust here, so like I can do it. But I would like to, for compatibility reasons, for people who are running on stable to be able to build this. So I'm going to go ahead and use the vector thing. So it's going to be vec, and I believe, actually let's use dash, let's get in that habit. There was like from length or something with capacity, that's the function. And this will give us a vector that is as big as we need. So instead of creating the array like this, we'll do vec with capacity, RAM size, and there we go. Or actually, might be a better way to do that than I'm. Oh yeah, of course we can use the vec macro. Thanks, move away 00. And then we can just use the same thing here. Yeah, but now I've created it as a vector. Now, like I said, unfortunately, this does mean that we don't need to box that anymore. Unfortunately, this does mean that this is actually resizable now. But again, I think it's okay because now we're going to be able to run this on stable. Yeah, so then when we run it, we're fine. I'm going to turn off the release flag here. Funsies. We're still good to go. Cool, so now we've modeled some kind of RAM. Yeah, move away 00 is saying what I was thinking, which is with capacity doesn't set the length. It also doesn't like actually fill it with values. It just says it has this much space already allocated, which is nice if you're going to fill the values really quickly afterwards. Then you don't have to worry about reallocations as you're doing that. So it's a lot faster if you know how big that's going to be. That's what with capacity is meant to be used for. Cool. So now we've modeled the fact that there is interconnect, which is some bits of the system that are together. It has some RAM. Right now, that's all it has. The CPU will be able to write to that. Eventually, the RCP is going to be able to write to that as well. That might be a bit tough to model in Rust, but we'll figure it out. One of the patterns that I used in my APU, actually, in the SNES audio unit emulator, is I did actually use pointers and unsafe to capture that mutability internally in the objects. And if you use it sparingly, I mean, it's okay because you can guarantee yourself that it's safe. But what you are doing is you are saying like, hey, Rust compiler, you can't help me here, and it won't help you, and that's what you have to live with. But you can do it here and there, and it's really not that unergonomic, and it's pretty good. Yeah. So now we actually want to get this thing to run some stuff. Let me just resize some stuff here. Yeah, so another thing that we're going to need to do is we're going to need to load that PIF and the ROM. Yeah, so the N64 is going to need to know about the ROM. And it's also going to need to have that PIF stuff in there. So what we're going to do is put the... We'll worry about the actual ROM later. The PIF, the boot ROM, is what I'm much more concerned with at the moment, and we'll worry about the ROM in a second. But what we need to do is get this PIF data into the N64, and the interconnect is going to end up owning that as well. So let's go ahead and open up N64. And I think we're going to end up creating an actual constructor instead of using default here now. No problem. It's going to return N64, where the CPU is going to be CPU default. And right now that's all it does, because we need to... Since the CPU creates the interconnect, I mean, alternatively, we could inject the interconnect into the CPU. I like that better. We'll do this. New. Then we'll do... I like that. So that the CPU will just accept an interconnect object, because I kind of like just doing all the creation here. I feel like that's not the CPU's job to create the interconnect. It needs to own it for mutability reasons, not for organizational reasons. So let's go open CPU here. We're going to have to remove default from CPU, which is somewhat a shame because then we'll probably have to write all these values again, but just going to have to live with that. Unless one of you guys knows a way that we can keep that, but I think we'll... Even window management. This is the problem with using a large font. Let's just make this the only file we can see. We can also do this. That's going to be helpful. Open N64 here. Actually, we'll open interconnect. Call function new. And this will accept interconnect. CodeSinger 001, is there memset alike in Rust? You actually can just use memset in Rust, but it's unsafe. And I'd rather write all the stuff out than introduce unsafe code if we don't have to. Just to let the compiler make sure we're not screwing that up. Which may sound really wasteful for a C or C++ guy, but I think that's the way to do it when we're doing Rust. Which is not that bad. I mean, it's not that much stuff. Let's have to roll this back. Zero. It's going to be CP0 default. And I believe like all the integer types and stuff also have default implemented, so we could write that up, but That's where I'm like, okay, we're all right. Pound reset won't reset the rest of this, so we're good there. Yeah, the interconnect. There you go. So that will transfer ownership here. You should return a new CPU, right? Yep, you are absolutely right. I wrote all this as if I had actually done that. And I totally forgot the scope. Good call. Yeah, so it will return a new CPU like that. Cool beans. Yes. Looking good. So the interconnect, this will own the PIF ROM. Let's go ahead and model that. PIF ROM size. I believe that was 2 kilobytes. 2048, yeah. 2 kilobytes. So that's going to be use size equals. And then we're going to do, yeah, that'll be good enough for now, actually. And then we can model our PIF ROM as, we'll do a vec for that too, of U8s. So that's nice. And yeah, so we will no longer use default here. We're just gonna implement interconnects. This will be function new. That's something we're gonna do here. Oh no, yeah, we don't need that because that's already handled. CodeSinger 001, there's an open RFC for type of T array : fill, which would be a safe memset equivalent. Thank you, I didn't know that. Actually, could you link that RFC? I would love to see that. Yeah, so this will take in the PIF ROM. PIF ROM is going to be a vec of U8. I'm not taking references here because we're going to transfer ownership. And so then the PIF ROM is PIF ROM. Uwe00 posted that RFC. So here it is. If you want to see it. Also, put all these links in the YouTube video description so we don't lose these forever. CodeSinger 001, I was thinking about using Rust for some networking stuff. Definitely would need box syntax and some kind of memset like. You would, unless you're doing immutable objects and creating them every time, which may potentially have a performance penalty, but then Rust is going to make sure that you initialize all your fields. So if you're worried about security, if you use a lot of the immutable objects and just create them again, you're going to be fine. But if you want to reuse the same buffers or objects and you want to do a memset on them, then yeah, that would be nice. You would definitely need that in that case. Excuse me, my voice is dying. So then when we created this interconnect, which we did on N64, sorry if this is getting a bit hard to follow. It's we'll be there soon. We'll create this with the PIF ROM, which will take in the constructor here. Or we could have the consumer of the N64 also create the interconnect, but I kind of would like to keep that. I think it's okay if the N64 creates that object. PIF ROM is going to be a vec of U8s again. Oops. And yeah, I started splitting this up on multiple lines because I like multiple lines, even though this was kind of ugly. Let me do that. That gets a bit prettier, I think. I probably forgot a comma. I did. I forgot one there. Failed to resolve undeclared type or module interconnect. That's because this needs to be aware of it. So we're going to use super interconnect. We get some mismatched types here. Because for the floating point stuff in my CPU, it said 0. We want 0.0. NC4, NC4 default, no NC4 in current scope. That's probably correct. So if we go ahead and look in main, I probably forgot to say, no, it's right there. Did I make that public? I did. Oh yeah, default, that's why. Gotta read the whole error. New, and we're gonna give it the PIF. New is private on interconnect. Make that public. I often forget to type pub because I like to not have things public by default and then like consciously make the decision to make them public. So it's more in the fingers for me to just type fn instead of pub fn, so I forget that all the time, which is probably not the worst habit. And there we go. So now the whole thing is put together. We have some kind of RAM. The interconnect from the CPU's perspective is also going to expose ways of reading and writing bytes or words. So we'll write that. And it's been 2 hours. We're still not writing code or actually running any code. But sometimes that's just how long this takes. I'm going to do another commit here. That is... Start modeling interconnect. Move away 00. When accepting a vec as parameter, always take it as a reference to an array of t, unless you really mean to consume the vec. I do mean to consume the vec. But I guess there's no real need to in this case to consume that. Actually, I do mean to, because I want to put it on this interconnect object. I want to transfer ownership to that. Otherwise, this PIFROM field here would have to be a mutable reference, right? Yeah, and you're also saying to pass the vec as %t as and your vec. Yeah, because that's the deref coercions. I actually recently asked a question about that on the Rust forums about how that worked. It's deref. Yeah, but I think I do want to consume this. Otherwise, this is going to have to be a reference to that, and I don't think you put mutability there. I do want it to own it. Otherwise, I told you that would have been a great call. It would only need to be mutable if it was self-modifying rights. I'm not sure I know what you mean. Oh, you mean, yeah, like writing mutable here. So it would need to be mutable. So in Rust, you don't have mutability on the object. So like in C and C++, the object itself is either mutable or constant, right? Or the thing itself. But in Rust, it's always the bindings that have constantness or not. I guess when you think about like pointers, it's kind of the same way with C and C++. But yeah, it's mutability on the binding. So like if I build how do I explain this? Basically, you wouldn't type mutable here because it wouldn't make sense for the structure to have that mutability encoded in it. It would make sense for the reference to interconnect or the binding to the interconnect object to have that mutability attached to it. So like in the case of PIF and ROM, you'll notice I didn't put mutable here in these bindings because I do want these to not be mutable. But I do create a mutable N64, but I pass in this immutable object. So I guess it's a bit confusing in this case because I do pass in something that was immutable when it was bound here, but I transfer ownership and kind of thusly the binding to this object. So this ends up becoming mutable, I think, when this starts owning it. But this binding is invalid in this case because we've transferred ownership. It's a bit confusing, and there are corner cases like this where it's a bit hard for me to explain because I would have to think about it a little bit more to give you a better answer. It's on the edges of my knowledge. But yeah, so we've built the interconnect, we built our N64 object, and we're going to make it run. So I think we're basically ready here. Let's go ahead and open up that CPU. Ooh, I have that down here actually. So this is how you do a forever loop in Rust. Right now it will do nothing except hang. Hang. So what we're going to do is this is going to be our loop where we're going to start reading instructions. There is one more thing that we need actually that I know we've actually skimmed over. Close the screen sheet. So it was in the power on reset because I hear the EC on the configure to start assign div mode pins. Because somewhere in here, in this procedure, it's going to set the program counter to the specific value that we talked about last time. And I think that's the last thing that we need to model before we can start reading instructions. Well, we need to do that, and then we need to make the interconnect able to actually read and write words. In particular, read them. We can do write as we actually run into that. So I'm not entirely sure. I can't remember where that address was. Borkmark says mutable cart ROM causes issues with the games that still have partner 64 detection built in. They'll think mutable space means the device is present and will hook the exception handler to code on the partner 64 and will crash your MU. I'm not sure what partner 64 detection is. Could you fill us in? Yeah, sorry, I'm getting a bit lost. Yeah, so what we need to do is we need to find out what that address was, where we're going to actually start executing code, and we need to, I believe, on reset. So I'm a bit surprised that this wasn't mentioned here in the power on reset thing, unless I just scrolled right past it. I can like look at like the Sen64 source and see where that is, but I'd rather pull it from the datasheet, just to show that on the stream. This is just showing like how you're supposed to pull the various lines high or low when you're actually going to do the reset. How the clock is going to be affected by that and which edges that's going to happen. It's not going to be under processor modes. All right, so I'm going to give in just for the sake of time and go look at the Sen64 source because that totally has this. Sen64. Oops, I actually don't want to lose that link. So I'll leave that there. GitHub. Sen64. Here we go. So that TJ90241 in the chat is this same TJ here. Cool of him to join us. So I believe it was like PIF address or something that it was in this emulator. Again, this info is going to be in the data sheet, and we did find it last time. I'm just being lazy and I'm going to look it up here. Yeah, it's right here. PIF RAM base address. Although I believe that there was like a B in this address somewhere. And I'm wondering if this is because of like virtual addresses and physical addresses. So that's going to be another thing that we'll have to model. But for now, I actually just want to, say screw it and just use like a 64-bit program counter and just use physical addresses for now. We can always change that later. But I am quite sure that that's, or I'm somewhat sure that that's actually not the physical address. I kind of want to know what that is. University Bicycle, I think last time we found it in some forums. I think you're actually right, and I remember that, yeah. N64 boot sequence. I believe it was this Emi-Talk thing. TJS, yes it is. RE virtual versus physical address. Yeah, that's a virtual address. Everything is 32-bit physical addresses. And I just kind of want to use the physical address for now. Yeah, here. BFC this. So actually what I'm going to do is I'm going to search this in the data sheet. BFC 0. Oh, he's saying 1FC whatever is the physical address. Interesting. That would make sense. But from the processor's perspective, this is going to be the address. But it would make sense that then you use the 1FC for your physical address. Because you would have actually modeled. By the way, for those of you guys who are unfamiliar with N64, I believe it is the only attempt at doing a full low-level emulator for the N64 out there. So in general, with details like this, at least the very basic details, they're gonna be correct in that emulator. So yeah, if he's storing that as that physical address, then that is gonna be the physical address. I do want to search this in the data sheet because I did want to find out where that was. Apparently I lost the ability to paste. Exception vector details. There we go. Of course, it's an exception. So the cold reset, soft reset, and NMI exceptions are always vectored to location BFC 000 in 32-bit mode, and they're prepended with all these FFs in 64-bit mode. The bus is a 32-bit bus, so it doesn't matter what these lines are going to be. But we could actually put the program counter if we're going to be using a 64-bit program counter to use all Fs here, and then we'll just mask that off. TJS says to look at the MMU chapter in the datasheet. It'll clear things up a lot. Cache versus uncached, exactly that. So I think what I'll do is I'll stuff this. Actually, I will actually go straight to that chapter before we decide on what we do here. It's funny, we're still not going to be running code for a little while, but this is just what it takes sometimes. So where was that chapter? So I see a cache memory. There's a memory organization, so that's probably what you're referring to. Yeah. Let's see if there's anything before this. No, that's something else. Cache memory. This chapter describes in detail the cache memory, its place in the VR4300 memory organization, and individual organization of the caches. This chapter uses the following terminology. The data cache may also be referred to as the D cache, and the instruction cache may also be referred to as the I cache. For those of you guys who are unfamiliar with caches, oh, he says 5.2. Memory management system, of course. We'll actually go there. But I will still explain what cache is. For those of you that are unfamiliar with cache, so in older systems, what you'll have is you'll have just like a bus, and all of your memory, like every time the CPU needs to read a byte from RAM or something, it'll just put an address on the bus, and a data thing will come back from some ROM or some peripheral or something. So put something on an address bus, puts a number on there, and then some data comes up on the data bus, and all that happens within a certain amount of time, and that's how you read and write bytes. when you're going at like low enough clock speeds or short enough wires, basically, um, there's a balance there. Um, then that's enough, right? Like you can just access memory directly. The problem is with more modern systems, and including this one even. Um, the problem is that your CPU and your memory are usually both really fast, but they end up being really far apart compared to how fast they are. And um, the consequence, or so the thing is that they can still both like, if you want to read 1 byte, like when you put that address on the line, it's going to take a long time for it to get to the memory, and that time is going to be like a lot longer than one CPU cycle, right? For it to get all the way there. I mean, for instance, I'm giving somewhat of a simplified explanation, but the thing is that so you can talk really quickly on that bus, and you can like pipeline a lot of memory, so your throughput will still be very fast. But the thing is that like if you just wanted to read 1 byte over a bus that's that long, you're gonna have to like put the address on there and just stall the CPU while that gets all the way there and all the way back, and that's very bad because you could have actually been operating, running more instructions instead of just sitting there waiting. So what we have is on the CPU instead we have something called cache memory, and what happens is that's a little bit of memory that's quite small, quite a lot smaller than your RAM, but it's in the CPU, so it's memory that the CPU can access extremely quickly. And so what happens is instead of whenever you need to fetch a byte, it goes all the way to RAM and come all the way back. Um, what it will try to do is it will say, well, I have this 4 kilobytes or whatever of memory in cache. I'm going to read a byte. Oh, hey, it's in my cache. I'm going to just read it from the cache instead of reading it all the way to the memory bus. You do, and that's of course a lot faster when it's in your cache, right? You do have problems, of course, if you try to read a byte that's outside of your cache, because the cache will need to be flushed and filled with new data, and that's called a cache miss. So earlier, someone was telling me, I can't remember who it was, someone was telling me that the way that I was organizing this code was going to be really bad for the cache on the host CPU, because our modern CPUs also use this cache mechanism. And one of the things that happens if you have a lot of pointers to a lot of objects, like in a row, and you start doing all that indirection on all those pointers, depending on when those objects were allocated, might be really far apart in memory. And all those indirections might cause cache misses every time you like go down a chain of pointers. And so that means every time you access one of those pointers, your CPU has to stall while that memory goes and gets fetched. Anyway, that's sort of a kind of a brief description of cache. As it's important to us, what we just read was that there was a data cache and an instruction cache. And this makes sense because the way that instructions are accessed is usually going to be fairly sequential. The only time it's going to break is when you have branches that are going to jump to some other place in the code. And modern CPUs employ something called branch prediction, which is where they, like a certain branch took one, like a branch could either jump to somewhere else or keep going. And so the first time that happens, the CPU basically stored what happened, and it will try to use that information the next time you get to that branch instruction to say, okay, well, I know this branch instruction is coming up while the CPU is being executed here. So let's go and load that memory to where that thing was going to jump to while it's coming up. So you can sort of pipeline the cache going and fetching data with the CPU executing instructions. And the whole idea is that if nothing is stalling, then your whole system is running a lot faster. Zorg 666, well, technically, because of things like out-of-order execution, the CPU probably won't stall on a cache miss. It depends on your instructions. It depends on how well your compiler actually moved those instructions. It depends on your out-of-order execution. When you really get down into, especially on modern CPUs, like really kind of hardcore optimization like this, a lot of things are really unknown, and you really just have to actually like try things and measure them to see how they are, because there's a lot of complex things that your CPU is doing to try its damnedest really to not stall any of this hardware. And it's similar to if you've ever done like optimization in compilers. It ends up being a really complex process because you have a lot of simple processes that are easy to describe on their own, but then when they sort of combine and act on top of each other, you get very complex results. And it's similar to what's happening when your CPU is actually executing code nowadays. I don't think that this CPU is going to be doing out-of-order execution. So I don't think that's going to be a problem there. But I mean, for the sake of an explanation of cache, yes, that is out of order execution, something you might want to know about. But I'm totally digressing, totally going off on a quite large tangent. Sorry for that, but somewhat interesting. So let's go ahead and just read through some of this memory management system architecture. Good way to spend a Monday night. The memory management system expands the address space of the CPU by converting a large virtual memory space into physical addresses. The physical address space of the VR4300 is 4 gigs with 32-bit addresses used. A virtual address is 32 bits wide in the case of 32-bit mode, and the maximum user area is 2 gigs. In the case of 64-bit mode, the address is 64 bits wide, and the maximum user area is 1 terabyte. For the TLB, which is, I think that's called translation look-aside buffer. I think we'll get to that when we get there. TLB entry format in each mode refer to this. So that's what that's going to be. Is it's going to be setting up certain data structures in certain parts of the CPU so that it will know how to translate different addresses. Zorg66 said, "Oh, I meant the host CPU." Yeah, modern CPUs are going to have out of order execution. The virtual address is expanded by the address space ID, ASID, for two figures 5.2 and 5.3. So let's look at those. Address space ID decreases the number of times the TLB flash, number of times of TLB flash when the context is switched. Have to read more to take all that in. The ASID area is 8 bits wide and is in the entry high register of CP0. The global bit G is in entry low 0 and entry L01 registers. So that's just telling us more about where actual data that this system uses is stored. So here we have an overview of a virtual to physical address translation. So the a couple things to clear up here for those of you guys who are having trouble following. A physical address is like an address that you'll put on the bus when you go fetch a byte. Code Singer 001, you probably won't have to worry about that as there won't be any context switches on the system now. Yeah, in this case there won't be context switches, and I'm not gonna emulate that kind of stuff in this emulator for a long time anyway. So yeah, don't have to worry about context switches. But I'm just reading the whole thing anyway. A physical address is something that's going to be on your actual data bus. They call it physical because like it goes on the actual physical wires. The virtual address is one that the CPU sees and all the code sees. So a code might refer to address, I don't know, to give a really small number, let's say it's address 2, whereas the physical address of that might actually be address 4 after some remapping is done. And the TLB, I need to double check again what that stands for. It's going to be a table of entries of this format that are going to say that, like, hey, whenever this address is accessed, either going out of or coming into the CPU, like from code, whenever code refers to this address, it's going to know how to do those translations. And the reason you want a table like this is so that you can actually write to them from code. So you can configure this, all this address stuff from the CPU itself. TJS, not so much the TLB addresses, but you do have virtual to physical translations everywhere in the IPL. Oh, I think that was a response to the context switches stuff. And yeah, the IPL is the initial program load, was it? That's the ROM that we're trying to run, the little BIOS. There's going to be a lot of virtual to physical address translations in there, or at least that we're going to have to worry about in there. So this gives us a little overview of how that address translation thing works. Let me try to zoom in on this a little bit. So we have a virtual address represented by the virtual page number. High order bit of the address is compared with the indicated area in this table. If there's a match, the page frame number, PFN, representing the high order bits of physical address PA is output from TLB. A lot of terminology here going ahead that I hope the rest of the chapter will explain to me as well, because I'm having a bit of trouble following myself, so don't feel bad if you are as well. The offset, which does not pass through the TLB, is then concatenated to PFN. So what that's saying is that we have these high order bits of this address, which I guess are used as keys into this dictionary, or some way to index this table. And then the entries in that table determines what these different bits are going to be. I think that's what it's showing here, is that we have, yeah, this page number here. What was ASID? Oh, that was up here. ASID, what was it? Address space ID. So a virtual address is made up of an address space ID, the virtual page number, and an offset. And the offset's going to stay the same, but the ASID and the VPN are going to be used together to look up an entry in this table, and that entry in this table is going to determine these first bits of this address, and the offset is going to be able to be used in that address. So like a virtual address is going to, like, the first parts of it are going to select like much larger portions of memory, and then the offset is going to be just a direct byte offset in there, most likely. A lot of this ends up being a lot to take in, just a lot to read about. Virtual to physical address translation. So converting virtual to physical address begins by comparing the virtual address from the processor with the virtual addresses in the TLB. So again, that's that lookup that we're doing. There is a match when the virtual page number of the address is the same as the VPN field of the entry, and either the global bit of the TLB entry is set, or the ASID field of the virtual address is the same as the ASID field of the TLB entry. So I guess there's this global bit that overrides how those table entries work. This match is referred to as a TLB hit, which is the second case. If there's no match, a TLB miss exception is taken by the processor, and the software is allowed to reference a page table of virtual/physical addresses in memory and to write its contents to TLB. So I think, very interesting. I think, so what happens is, it looks like at the start of execution, this TLB is actually empty, this table, and then you'll just start like writing code. And as soon as you address a memory, like an address, then it will start checking to see if that address is referred to by any of the entries in this table. Because that table would be empty, for instance, we would have what's called a TLB miss. That will cause an exception, which means execution is going to temporarily start somewhere else in the code. And in that exception, it looks like you'll be able to in that exception, it looks like you have access to where these tables are in memory or something, and you can write that in there. A bit confused at how all this works, so if I'm wrong or if I'm ranting, bear with me. If there is a virtual address match in the TJS says MIPS has these weird kind of wired TLB entries that don't change, but they're not referred to as TLB entries. Something to watch out for, I guess. If there is a virtual address match in the TLB, the physical address is output from the TLB and concatenated with offset, which represents an address within the page frame space. The offset does not pass through the TLB. Yeah, we understood. The lower bits of the virtual address are outputted as this. That makes sense. And then we had 5.4.9, virtual to physical address translation process. During virtual to physical address translation, the CPU compares the 8-bit ASID, if the global bit G is not set, of the virtual address to the ASID of the TLB entry to see if there's a match. One of the following comparisons are made. In 32-bit mode, the higher order bits of the virtual address are compared to the contents of the TLB entry. VPN2, which is the virtual page number divided by 2. In 64-bit mode, the higher order bits of the virtual address are compared to the contents of the TLB entry, so it's the same thing in both modes. TJS is just giving more good warnings. If a TLB entry matches the physical address and access control bits, C, D, and V are retrieved from the matching TLB entry. While the V bit of the entry must be set for a valid translation to take place, it is not involved in the determination of a matching TLB entry. Figure 5-19 will illustrate the process. Okay, that's why it wrote this twice with stars. The number of bits differ depending on the page size. Interesting. It couldn't be simple. So we have the virtual address on the input, which is the virtual page number and the ASID, which I forgot it was again. Takes me a while to learn things. I'm a bit slow. Then it asks for an user mode, because I guess this is the CPU would have been used in a lot of systems that would actually run an operating system. Yeah, so here, if we're not in user mode, we are in supervisor mode, and there's not a legal address, we get an exception. Actually, let's forget all this stuff for now. We'll go this way. Let's assume we're in user mode. The address. Okay, so either way, if the address is not legal, we're going to get an address error exception. If the address is legal, in any of these cases, let me see if I can zoom out a little so we can see more of the flowchart. So it doesn't matter what mode we were in. The address was legal. Then it says, is this a mapped address? And I'm guessing that was if it ends up matching one of the TLB entries. Yeah, because here are all the different cases about whether or not it was a match, and the different kinds of exceptions that could happen with that. CXMU2, okay, let me interject here. You cannot write an emulator by reading a book. No, we cannot write an emulator by reading a book, but we can gain the knowledge that we need to write the emulator by reading the book. And I understand that might be maybe not the best stream content, but still got to start somewhere. I wanted to show the full unabridged process in this series, and I think that that's what we're getting here. CXMU2, do you know who I am? I do not know who you are. TJS says page 134 in section 5.2 is a better starting point. CX72 is linking a YouTube video. I will bite. I didn't quite see how that was relevant. Page 134. CX72 is pointing at the CMIPS runbook. I did get that last time. We could start looking at that as well. I do appreciate getting that link again, because it is something that we'll need to look at. And I've heard also from Daniel Collin, who I mentioned earlier, that was giving me a lot of those tools, that was actually a really good resource. But I do get the hint. We either could continue reading this on stream, or I could read it off stream and then come back in a different segment, and we could go over the stuff that I've learned. Because again, this stuff is new to me, and I need to learn it myself, and may be useful for you guys to see the process of me learning it. May not be. And Rusty Bicycle says might be a good idea to collect some of these links in the README or GitHub wiki. That is a great idea. I will remember that, and I will actually put that in my notes right now, and I will totally do that. Collect all this info in the GitHub project wiki or somewhere. Codeslinger001, I'm finding it quite interesting personally. Ryan Hebert, me too. CXMU2, don't stop. Appreciate the support, guys. Yeah, so TJS says don't pay attention to the TLB mapped section. Look at the TLB unmapped things and how they're used. CXMU2 says, but if I were you, I'd implement the RDP before you do the actual emulator. So a lot of other emulators have like plugin based architectures. So if you wanted to just implement like a particular part like the RDP, you could totally do that. And you would end up skipping a lot of these details at first, so you could get to sort of the meat of the emulator portion. But at the same time, I kind of want to write the whole thing because I would like to learn all this. So I think I'm going to continue working on this. Even if we get to run code a little slower. It creates tension. Ernest, so am I. I'm learning a lot. Without this whole process, I'd be lost in the code. So, yeah, glad you guys are getting something out of me reading this book. I'll continue reading it instead of getting lost in this. So TJS did tell us to look at the TLB unmapped things and see how they are used. Is that further down, or you did say that one page? That was at 150, 134. Yeah. So I'm a little confused at what this table is telling me. The VR4300 internally uses 64-bit addresses. In the 32-bit mode, a 32-bit value with bits 32 through 63 sign extended is used as an address. So I guess that just means the bits from 32 to 63 are going to match the 31st bit. That's usually what that means when it's sign extended. Normally, the program in the 32-bit mode uses 64-bit instructions. However, there is a possibility that an integer overflow may occur as a result of an operation of base integer plus offset to calculate an address. So I guess if you had a memory map segment that mapped to like the end of your address, and then you had an offset that like went above your address space, and that integer would overflow or went above 32 or 64-bit or whatever that was. TJS says this table is telling us how virtual TLB unmapped addresses are translated to physical addresses. So this is like, I guess, when things are not mapped by the TLB, when things are not set up in those segments in that table, this is how the addresses are going to be interpreted. CJS is saying that 0x BFC followed by a bunch of zeros translates to an uncached physical address of 0x 1FC0000. These are the kind of things that you need to understand to get past the IPL. Okay, I think I just realized something that this was telling me, um, or what one of the things TJS is trying to tell me, is that this table is fixed, correct? And then depending on where these addresses are in this table, that will either get mapped through the TLB or not. Yeah, Codeslinger 001 I think is catching on to that as well, because that's what he's saying here is that 0x BFC0 is going to be here, and this is 0.5 gigabit or gigabytes area where the TLB is unmapped and the memory itself is uncached. So that means the memory accesses that you're going to go through here aren't going to affect the cache. TJS says yes, so I guess we're on the right track. Okay, so I'm not entirely sure. What was this table called? I kind of want to know where in the datasheet that it told us this, just to fully understand where this is coming from. So this is figure 5.6, and that was referred to here. Okay, it's actually just right here. Kernel mode virtual address space, and we're going to be in kernel mode when we start up, is divided into regions differentiated by the high order bits of the virtual address, as shown by figure 5.6. Table 5.3 lists the characteristics of the 32-bit kernel mode segments, and table 5.4 lists the characteristics of the 64-bit kernel mode segments. Yeah, but the point is that, so when we boot up and we're in kernel mode, which is what happens when we turn the processor on, we do our power on process, it looks like that we're going to have these things here. And I think this is actually what TJS was also referring to when he said it had like these hardwired, what did he say? I want to get his words. Let's see if I understand it. Yeah, MIPS has these weird kind of wired TLB entries that don't change. They're not referred to as TLB entries. And I think that that's what he's talking about here now, is that when you start up in kernel mode, you have, or I guess a lot of this probably also applies to, well, I guess when you're not in kernel mode, then you're probably always going through the TLB because you have virtual addresses only, I'm guessing in that case. But in kernel mode, you have access to everything. And it's going to have these hardwired sections here where all this stuff is already banked off. And in those sections, you have these various, like you can see, these are all these big, various attributes is what I'm trying to say. So in this case, this address space is TLB mapped. This one is TLB mapped. This one is TLB unmapped and uncached, which is why you would put a boot ROM there, because you don't necessarily want that going into your cache, because if it goes into cache, it can get out of cache. And you wouldn't have had it. You would have had it TLB unmapped because none of that stuff would have been set up yet. And then, of course, this one is TLB unmapped, but it's cacheable. And then this whole thing is TLB mapped. And I'm going to probably also assume that that's cacheable. Maybe not. Maybe only this was cacheable. Actually, this probably would say cacheable if that were. So this is probably the only cacheable portion of memory, which is interesting. Yeah, TJS is clarifying the TLB mapped and TLB unmapped stuff. If you access an address in here, then you'll get TLB unmapped and uncached memory from the CPU. Parts of the address space use the TLB as you would expect. Other parts are hardwired, and this table is telling us exactly where that's the case. MoveAway00 says, okay, so if you request memory at this address, you would get uncached physical memory at 0. So And if you access it here, you get cache memory at 0. So what I'm a little bit confused then is where you're getting that 0 from, right? Because each TLB entry can specify whether or not the region. Okay, that's another thing that TJS is telling us, that if one of these is going to be TLB mapped. Gotcha. Now I know why you're saying that, because I was saying that if this were cacheable, it would say so, but that's not the case, because the TLB can say that a particular portion is cacheable. So you'll notice in this table, it says all these ones are either TLB mapped, and it doesn't mention if they're cacheable because that's irrelevant, because the TLB will specify that. Whereas here, these sections that are TLB unmapped, it mentions that it's uncached or cacheable. And that's because you're not going to get that information from the TLB, so you end up getting it from which one of these segments that you access. Okay, now we're actually getting some kind of progress here. Appreciate you guys bearing with me while I learn this. And again, TJS, thank you so much for helping us out here. But again, I still am a little bit confused at when you access this address here, this starting with A, you'll get physical address 0 that was not TLB mapped and it's uncached. And so CodeSlinger is saying that that address minus, of course, the base of the section is 0. So I'm probably just getting lost in the details, but I guess somewhere it mentioned that the actual physical address you get is going to be this address, this virtual address here, minus the start of the segment, because these are the different segments, is what these different entries in this table are. So where was that mentioned? Because yeah, what he's saying is that like if you access this address, then it's going to be physical address 0, not TLB mapped and uncached. It's going to be 0 because you always subtract the base of the segment. What I'm missing here is kind of where it told me that, just to get that information in the datasheet's words. And I guess there's some other stuff here. But it just told me that earlier. If we go back here, okay, I'm guessing that might have been the address space ID. Table on page 136. Oh, so here we actually get the full segments here. So what this is, this notation here, if you're unfamiliar with seeing this number colon another number, that's pretty common in like hardware stuff. That means that's those bits of this A, and this A, I guess, means address bit value. So if the 31st bit of A is 0, then all these will apply. CodeSlinger001 says, there we go, that's the money shot. So what this is telling us here is that depending on these different parts of this address value, because like if we're going to like read a byte from a virtual address, and that's going to be a 32-bit virtual address, I understand. Depending on which of these bits in this address are set, those will apply to these different kernel segments. And then we saw actually how those were laid out in that other table. We get the virtual address, which is what this ends up being because of these bits. And if you just use these bits in this position of 32-bit number, you will get these values, these value ranges. Then it's showing us, okay, these segments will be TLB mapped when you go to the physical address space. Or in this case, in particular, this is the one where the TLB is mapped. We get these addresses in the virtual address, but they will be mapped to these physical addresses with no cache and no TLB mapping. And what was the other? It was right here, actually. Yeah, no TLB mapping and uncached. And then it just shows us the size of the segments. Okay, so a lot of reading and a lot of digging and a lot of help from TJS and some tips from other guys as well. So thank you guys a lot. But it looks like we have in this table, these are sort of this is sort of like hardwired the first part of the address translation when we go from a virtual address to a physical address. The first part is going to be this. The second part, if necessary, is going to be the TLB map, which just means if we're in one of these segments, it means we have these virtual addresses. So if we're going to take one of these virtual addresses, for virtual addresses in this range of values, it's going to be TLB mapped. So then we're going to have to do a second stage where we translate the virtual address to a physical address by looking at entries in the TLB. Whoo! TJS. So now hopefully it makes sense that the processor starts executing at 0x1BFC000, which maps to an uncached address of 0x1FC0000. If you look at the N64 memory map, this happens to be the PIF ROM. So I actually want to pull up the N64 memory map now. See if we can find one. Here's some images. And this first one that we pulled up, this is literally the second image. Let's look at the first one to see if that actually had it as well, just because it was kind of funny. Now this second one was a lot more illustrative of what these guys are trying to teach us. And that is that here we have the virtual space here, and here's the physical space. And I'm guessing a lot of this stuff, it's not going to use the TLB unless the actual cart ROM uses that, and we may have to deal with that then. But yeah, the execution will always happen at. Yeah, this image is just perfect. This is really funny. So if we start executing at 1BFC0000, or sorry, FPGA Nega actually also links another memory map, which is, wow, okay, this was, gonna check this out. This was very detailed. Codeslinger says, my guess is that the PIF will set up some of the TLB because that's how OS kernels do it. So my guess, one of these guys is gonna probably pipe in here and give you more information than I will. But my guess is actually that the PIF won't necessarily do that because I don't think there's going to be enough of like a kernel here for that really to make sense. Like I don't think there's going to be a kernel mode and a user mode stuff, so I don't think the kernel will need to set that stuff up. The PIF would do that if like the programs in ROM assumed a specific configuration, a specific like address space. But I think what I'm saying, Codeslinger 001, is that I think if we were running an OS on this, then that would actually make sense. But I have a feeling the PIF won't actually do that because I think these programs will run bare metal. Borkmork says carts will initialize the TLB shortly after boot if they were built with official libs, even if they don't proceed to use it. TJS says I'm correct. So that all that makes sense. I'm really happy with how much we're learning here. This is cool. So yeah, so if we look at this memory map in detail, the address we were told to look at from TJS again is 1BFC 0000. And that's going to be up here. No. I bet there's going to be in the detailed map, I bet it's going to be in here. Let's actually search 1BFC. That better not be case sensitive. It wasn't. We may not get that address specifically, but I want to look at the... Oh, okay. No, this says cartridge domain. I missed that. That's actually reading from the cartridge, I think. Yeah, that's what move away is saying. Careful, the sheet has memory map and cart map. And FPGA is correcting the address. It's BFC0. That makes more sense now when I'm looking at that address. That was fairly confusing. Where I mapped that. Yeah, so if we search this, or 1FC0. Yeah, right here it says PIF boot ROM. The start and end right here at 1FC0. And this I'm guessing it's telling me is a physical address. And that would make sense that this memory map here would be showing us that as a physical address. And you would have to understand, as someone who's writing code for this, that if you wanted to address that, you need to go through the virtual addresses of MIPS and all that other stuff. So 1FC0 is where this PIF ROM is going to be mapped to, and that's where we're going to put it in our interconnect. And then our address translation, which is going to happen in the CPU, is going to end up getting there by setting the program counter to, because that's 1FC, so it's going to be BFC 00000, and then going through enough translation to understand that's going to be in this kernel segment. It's going to be mapped here. MoveAway00 says, so should the CPU be in charge of the virtual physical mapping or the interconnect? That's a really good question. In this case, it looks like it's going to be the CPU, because this whole data sheet we've been reading is all about the CPU, and I'm guessing the CPU handles all this internally. I think the block diagrams we saw earlier said that this was all self-contained in the CPU chip. In a lot of other systems, this is handled in other chips. I know the PS1 handles this in one of its coprocessors. So I think, technically, I think this happens in the CP0. I think that was the whole thing, but the CP0 was integrated into the CPU. It's technically a coprocessor, but it was on the same silicon, I guess. Again, someone correct me if I'm wrong, but I think that's what we've learned here through all of this trouble. Thanks again, guys, for helping clear this up. Oh, wow, it's 10 already. Let's keep going. So what we need to do is we need to set the program counter to that BFC0 value. I'm just saying the first four numbers because it's some zeros that we don't necessarily need to run. So all of this was to see on power up, what should the program counter be? And now we know. So on CPU power on reset, it will call the CP0's reset, and it will set its program counter. Move away, it's 1 a.m. here, CodeSlinger001, same. Thank you guys for staying up with me, fighting sleep, I guess. Reg PC. I'm guessing also we determined that the PC was going to be 32 bits. I guess that depends on if you're in 32 or 64-bit mode. Let's just set it as 30 as this one number anyway. BFC00000, and that will give us our start address. I might move that to a constant, but I don't want to name that constant, so I'll just write a note for myself anyway. And then we'll have to implement some addressing when you start reading this. Guys, we are so close to running code. Borkmork, as a note in cart domain is that the doc is a bit confusing. The domain refers to which of the two settings, domain 1 or 2 of PI is used to translate the address. Cartridge domain 1, address 2 is your normal cart space. I'm a little bit confused what PI is in that case. Could you clarify that for me? A little more caffeine. So what we're going to do here is we're going to read a word, right? And a word is going to be, I think word's the right term. A PI is peripheral interface, cartridges and stuff on that bus. Oh yeah, gotcha. The peripheral interface I think is part of the N64 specifically that actually connects to stuff on the cartridge bus, which is either going to be ROM or whatever the cartridge has in it, I guess. Borkmark says that's correct. Yeah, I'm just going to say, so let opcode, getting so close, guys, is going to be read word of the program counter. So we're going to go and read a word, and read word is going to be a function that we'll define on self as well. And again, someone yell at me if word is the wrong term there, but I think it is. Even though that may be confusing, because I always think of word as 16 bits because I'm used to x86, but I think that's more correct for MIPS. We'll just do that here. Fun read word. We're going to take an address, which is going to be a U64 until we decide we know better. And then that's going to return U32, because that's how big our words are. Yeah, and Rusted Bicycle says word is whatever it is on that machine, so I think using word is correct here. 32-bit on N64, so it looks like we're on the right track. And again, I'm probably wrong about this address being 64. Like I've learned nothing from all of this. I'm actually going to make those U32 because I just do think that that's what this is going to be. And it's going to take a while for some of that information to sink into my head, at least. But we'll, as we work with this more, we'll become more familiar with it, and that'll make sense. So we're going to read the word. This is where we actually will access the interconnect. Kittens, yay, code exciting, finally, after all this. It's going to be so great when this whole series is done. I just start telling everyone, dude, just start at episode 4. Just don't even bother. But thank you guys for sticking with me. I think this is really fun. Read word. So we're going to read from this address. So now we're going to have to translate that address. So here's what I want to do. I want to say if... let's actually do this too. Function virtual adder to physical adder. Virtual adder U32. TJS corrected me. We are going to make this address 64 bits. Because of chat delay, I don't think he saw me screw that up. Yeah, so the program counter, as he's just told us, is that it is technically 64 bits. The address gets sign extended, that BFC, because that top bit is set to 1, so all the other ones are going to be Fs. Yeah, good to know. So actually what we're going to do, I'm totally going to model that. And I believe Rust allows us to put these underscores in here, which is going to help. Get it look nicer. Yeah. So we're going to do let physical address is virtual address to physical address from the adder. I'll rename this virtual adder. Let's call that virt adder just to make that a little easier. It'll look nicer against phys adder. And here I'm just gonna explode if it's not one of these regions that we recognize for now, because I really want to get to running code, and that'll be nice. Kittens, I also really enjoy seeing someone use Emacs. A lot of people use fancy IDEs or plain text editor. I tried to use Emacs, but it seems to have a huge learning curve. Actually, a little bit about that. I'm going to go on a bit of a tangent, guys. Sorry, I'm going to put off running code a little longer. So I up until about May of last year was just a total Windows guy and Visual Studio guy, and that was my world for a very long time. And then for work, I ended up having to get a Mac because I was giving a lot of presentations in the Bay Area, and it's kind of an image thing that you kind of need to, I guess, have a Mac. So I got one of those, and I started just like trying to use Xcode and stuff, and I felt so useless, especially because I wanted to write code in like Haskell or Rust. I wanted to play with Rust at that time, and so because I felt so useless, a buddy of mine was using Emacs, and I always liked how he could just do everything from the keyboard. And so because he was using Emacs, that's why I chose that over Vim, just because I knew someone who used that, and I just hammered on that. And man, I went for months before I could like do anything useful in this editor, like honestly. But now that it's been a while, I am super happy that I switched to an editor like this. And I would totally recommend someone who writes as much code as or writes a lot of code at least, to look into this. Gunslinger 001. That's why anyone chooses anything. It's true. I mean, it's your friend had it, so you had it. Most of the music I listened to growing up is because my brother liked it. Move away. Although for us Vim users, give Spacemacs a try. It's Emacs with Evo mode and a bunch of nice defaults. I have heard that that's super good. In Rusty Bicycle, Xcode is useless. If anyone knows how to write OS X drivers without Xcode, I would love to get information on that, by the way, because that's the only time I ever use Xcode anymore. Virtual adder to phys adder. So let's actually do that translation. So here, we were going through here. We're going to also incorporate the sign extends into this 64-bit address. So if vert adder is, yeah, these are unsigned, so this will be okay. A000, and the virtual adder is less than, let's put this up. Was it BF? Yeah. I didn't like how that got split the things there. CodeSlinger 001. You can do drivers in Emacs, but you need to drive it all with Xcode tools anyway, so it's actually worse than just using Xcode. That was my understanding. Is that the actual code portion isn't that much more difficult to write in Xcode when you're doing those projects. They don't tend to be that enormously big anyway. Just FYI, bottom 8 lines are covered by my overlay. Oh yeah, with my face. Thank you. I'll open it up over here. Thanks. Did not notice. Yeah, so now we can read that. And then if this is the case, then we're going to, yeah, just sub A00. So we're going to return vert adder minus this base address. And actually, I don't use return here or any semicolons because I'm going to have this if expression just be this value. So otherwise, actually we usually write this in Rust. Otherwise, I'm just going to panic. Why not just shift 29 and test for double equals OB101? That would be shorter in code, but I'm not sure it will be as explicit. I don't think that would be as easy to read. Actually, though, according to this part of the table, it would be easier to read. So maybe I'll do that. I like that actually. Let's do that. Let adder bit values, and we can get this exactly here. Is vert adder shift right 29. Yep, that was the case. And so now we can say if adder bit values is equal to 0b101. Comment to that section table name so it makes sense later. Good call. Good call. What was this? What was the title of this? I'll just say the processor user manual, actually. And where were we in here? 136, I remember the page number now. 131 actually is the important one. So I don't remember the page number. Yeah, and there's the mask, of course. Yep, good call, guys. I'm so used to working with 32-bit that I actually totally would have noticed that, so glad you guys are here. And so, yeah, so we'll just mask that off. It was the lower 3 bits, so, and 0x07. Actually, let's mask. I like this better. OB111 because we're looking at those bits. A little more expressive. So table 5.2. It's like pair programming with 23 people. 24. I'm still here. I'll just say CPU datasheet. Or actually, I should really say this. VR 4300 user manual. I'll leave it at that. I think it's next one 5.3. You might be totally right, and that's good call. Table 5.2 shows the features of each segment, and I think that's this. So I think this was 5.2. Maybe I'm wrong. Oh, that's not the table from before. That's 64-bit one. Oh, yep, you're totally right. You're totally right. You guys got it. Nice, nice. 32-bit right here. 5.3. Yep, correct. Good. Good, good, good. Yeah, so if this is in that range, I'll also address that. This is going to be case like 1. Then we're going to yeah, no, we'll be fine if we do vert adder minus 0x fff fff. Yeah, then we'll return that. Otherwise, if it's not in other segments, what to do? And panic here. And yeah, unrecognized virtual address. And we can print that. It will probably be nice to print this in hex. Ernest, gotta go, guys. Thanks for the stream. Ferris, keep the good work. See you, man. Thanks for joining us. This will all be on YouTube, so you can watch the rest later. Recognize a virtual address. So if anyone can remember how to print hex values, let me know. I'll move on and then I'll put that back in later because I always forget these. Formatting in Rust. Yeah, so we'll get the physical address and then we'll actually read the byte. Move away says :x prints hex. Lovely, thank you. I'm going to stick a 0x in front of that, just so we know. Unless that will also prepend that 0x, so yell at me if that's wrong. So let phys_adder is virtual adder to phys_adder. Yep, so we get the physical address, and then we're going to actually read it. So then we go to the interconnect, so self.interconnect, and then we're going to read a word from there. But now we give it our physical address. And the interconnect, I'm going to make the address 32-bit because it's a 32-bit bus. So we're kind of seeing how this all fits together. So this is going to have a pub function called readWord. Remember, we're also going to do a write word later, but that's okay. Oh, and here we go. Actually, if we put a hash here, it says move away 00, this will print hex with a 0x prefix. Awesome, thanks guys. So we're going to read word on the interconnect, and we're going to take the address. We don't need to specify virtual or physical because it's assumed to be physical if it ever got to the physical layer here. That's going to be U32, 32 bits. And we're on a roll now, guys. We are going to get to code tonight. I'm determined. Then we're going to actually read the word. So now this is where the N64 memory map comes into play. So yeah, this is where this particular bit of hardware is going to be addressed. So let's go ahead and find that N64 memory map again. I wanted to find this one because this was pretty funny. That wasn't detailed enough. We need this one, and of course it was this here, PF from start and end here. So here I'm actually going to compare these addresses directly. So we'll move those over here. 1FC0. I'll open this over here. I'm going to close this, close over here, open up the interconnect here. And so now, if adder is greater than or equal to 0x1fc0 and adder is less than 0x0, 07 bf, and I'm going to add a little note to do replace constants. Useful names, so we don't forget. So if it's in this address space, then we're going to return a word from the PIF-ROM. So this is where things get a little bit interesting as well. Because what I'm going to do is we're going to read a whole word, which means we need to read 4 bytes. This is where our endianness comes into play. And I think what I'm going to do is I'm just going to do 4 byte reads and then hook them all together. And then handle the endianness here. Oh, TJS, less than equal. Yeah, of course, 7BF. I actually want to do 7C0 and do less than because I think those are nicer numbers. Because then we can do the end as the start plus the size of it. That makes me more comfortable. Good catch, thanks. So when we actually read the word, yeah, we need to read the 4 bytes. So we're going to return PIF-ROM adder, and I'll probably get the endianness wrong here. But I just want to throw it together now to do check endianness. And we might also, again, because when we read here, because I believe actually yeah, subtract the base. Good, another good call. Relative address is going to be adder minus, and another motivation to replace that with a constant. Yeah, TJSC, you meant less than equal to. I understood that, but I would rather have just written this 7C0 and done less than, because I like to have the end address be the address that it's, yeah, now you get it. A Silenter Orchestra. You might be interested in the byte order crate. Oh, I forgot about the byte order crate. That's the burnt sushi's crate. I do remember looking at that. For reading, writing numbers in big endian, little endian. Yeah. I think for now, just for speed, I think we'll just like hard code this process here. Because here's what I want to do when I read this. I want to read it in. I feel like the interconnect, if you want to be really correct, would just read it in as like some random endianness, and I kind of feel like it would be. Maybe I'm a bit confused because when I think about the actual hardware, the lines are coming off the CPU, and the way that those are going to be, bit confused. Avoid 00, maybe N64 should copy PF to its memory, then you don't have to special case it. That's what I was thinking, the same thing. That's the baller move. I'm not going to do that. You could do that to make it faster, but then someone could like overwrite those values, which would not be technically correct. I don't know. It feels like to me. I'm going to special case. Yeah. We're also going to do some potential overflowy things, but here's what I'm going to do. I'm actually going to just return it as big endian here. So that means the first address is going to be the largest, so we're going to shift that left 24. We also need to do a cast here as U32. Read word is going to return a U32. And that, or that, geez. So this is going to feel a bit hackalicious, but it'll be good. And I know that we can totally overflow here. It's going to be okay. 16, 8. To do by order crate seems a better way to do that there. So we'll just do that as a big endian read from here, and we'll worry about the technical details of where that big endian read would have happened. Because I'm guessing the hardware would have had to do this as like 4 consecutive. Well, I don't know how big the data bus is. If the if the data bus is 32 bits, then this would have done this all at once. And then I guess this would have just returned the value in some representation, which was, if it's just the raw bytes at the different addresses, yeah. What matters with these numbers is how we're encoding them. And then I guess the byte order crate would help too, because it's like here I'm kind of assuming that the host CPU is little endian when I do these shifts, whereas the byte order crate can solve that. So I'm just going to leave this to do here, and we're going to go with this, just so we can get code running a little sooner and just stop thinking about this, because getting a bit locked up in details, I tend to do that. Anyway, so we're going to read the word at the physical address from our CPU again. And what this is going to give us is opcode. Oh, no, wait, no. Sorry, I had that wrong. I had this right. All it's going to do is return the byte read from the interconnect. Then opcode up here is what actually read that word from the PC. There we go. A strange enigma. I'm a computer science who's really interested in getting into this stuff. I have no real experience with programming this low level. Does anyone have any advice for classes to take / projects to get my feet wet with this kind of thing? I've slowly been teaching myself C to get used to memory management, pointers, etc. My advice would have been to learn C. Yeah, and Rusty Bicycle also recommends assembler. I actually agree with that. So I kind of went a weird route with that. I got involved in the demo scene at a really early age, so I was doing a lot of like graphics programming, and a lot of it, I did before I really understood C and C++ very well. But I ended up really liking the low level stuff, and I spent a lot of time uh, working on demos on like older platforms, and I've done a ton of C64 code that I'll never release, and it felt kind of weird, being 18 and buying a C64 in not that long ago, and my friends all thought it was really confusing, but what really captured me about that is just like, here's a system that I could totally understand with a fairly simple assembly language, and I can make it do really cool things. And I think there's this really nice hackability about these old machines where like you can code assembler on them, and it'll work, and you can like they're just really hackable. And so I really liked doing assembler on old machines. If you have a machine with XP, you can write little DOS programs that can maybe do graphics or something. Anyway, I second that C and learning assembler stuff. I think that's cool. I don't know. I don't think I could recommend what kind of classes you would take. I dropped out of college, so I don't really know what kind of courses they offer at that level. As far as projects to get your feet wet with this kind of stuff, man, write an emulator. You could totally write like a NES or a Game Boy emulator, or even like Chip 8, and then you could totally start understanding this stuff. Codeslinger 001, yeah, no load and store buffers on the Z80. And C64 was 6502. Spectrum was Z80. Codeslinger 001 says classes won't cover this kind of thing, which is unfortunate. I think computer architecture students cover that. I don't think computer science does, because I think computer science is about like writing good code. Or like, I need to define good code if I say that. Like writing expressive code and understanding higher level concepts. Whereas you wouldn't be this low level with stuff unless you were like in computer architecture, I think. Yeah, I don't know, but that's my good feeling. Codeslinger 001, yeah, I grew up with Sega Master System. If you take assembly in CS, you'll end up writing a serial port adapter. But you'll do it in assembler. So, up to you. Okay, so we're here. We've read we've read a word, and now we're going to get the opcode. What I'm actually going to do, Strange Enigma, you're welcome. If you take assembler in EE, you'll end up driving a microcontroller to power a traffic light. So true, I bet. That's pretty funny. Okay, so now that we've got our opcode, what I actually want to do is I want to print this to make sure that we've gotten it right. And the way I'm going to do that, I'm just going to panic. This just for now. Do the opcode. Yeah. All right, so now we have to fix some stuff. I forgot to write self here. I do that all the time. That is like my most common bug when writing Rust. Self is not available because we don't have a self argument here. Read word is actually don't need a mutable self. I'm guessing that's going to be the case here as well. If you're wondering what the difference between and self here and mute self, in Rust, so in C, when you add a method to like a class, inside the method, the this pointer is explicitly going to be there, and it points to the memory where your object is. In Rust, what you do is you explicitly add a parameter to take yourself. Right, to take this self object. So self is this effectively, except it's an object. So like if you dereference the this pointer in C++, you would have the same thing as self. But of course, I'm taking a reference to that, so I'm back to a pointer again. But anyway, the mutable reference to self just means like, oh yeah, so I can change self here. If you don't put mute there, then self is mutable. So it's similar to making a const method if I don't put mute. Well, technically, to control the traffic light, if you try to power it from the pins of a microcontroller, you'd end up with a lot of smoke. Yes, you would. You guys are great. Okay, so we're just gonna panic with the opcode. Resolve name vert adder to fizz adder. That's probably because I didn't do self here. Now we have the trait index u32 is not implemented for the type vec. Oh yeah, because we need to do it as u size. Let me cast all these. Not a problem. As u size. Now we got some mismatched types. We expected something that was going to return the ads here. It was saying that it expected unit, which is basically the return value of a void function, but it got a u64 as a return value here. So it was complaining this, where I was trying to return something that was going to be u64, where because I hadn't specified a return type, it would have implicitly been unit. Those types don't match. We're going to return u64 there. We are going, what is this? Self-incorrect read word. Yeah, we need to as u32 here. Giving us lots of type errors, which I like. Again, it looks like I did the same mistake in the interconnect. Maybe not. Error if maybe missing an else clause. Yeah, no, that's actually totally the case. Because here we return a value, and then the because this expression is going to have this type now, we need an else clause. That's okay, and we're going to basically do the same thing here. Same thing as here. And better. All right, yeah, there we go. So now when we run it, we got a lot of errors. And then at the bottom here, thread main panicked at opcode, and here's our opcode. So now I want to look at our disassembly again. Here. And you'll notice, I hate that I can't scroll in this. Let's pull this over here. This says 3C01A460. Whoops, was that the beginning? No, there's the beginning. 3C093400, and our opcode was 3C093400. Boom, so at least we read the op. So we've read a word from the PIF. It's a match. Cool, so now we're gonna do what it says. And finally, we've at least accessed code. So I'm gonna do a little commit here. Been a good ride today. So yeah, started reading opcodes. Good game, internet. Okay. Now we are going to actually interpret this opcode. So we've read the opcode, and where were we? Here. Here's what I want to do. I want to match on the opcode. Kittens, apparently I have a huge delay. There is definitely a chat delay. Like if I type something in chat, you guys won't, the video won't catch up till later. Maybe other delays as well. I think different people on different things. So CodeSlinger says the opcode is the top 6 bits, which we did read yesterday. I think op word. Let's do that because it's the full word. And then we can do this. We can say let opcode, and then we can get those top 6 bits. Now here we know we're working with a 32-bit value. 32 minus 6, if I can do math, is 6. So we're going to take the op word, shift right 26, and we're going to mask off the top 6 bits, which is correct, I think. And let's match on that. So match is pattern matching in Rust. You can, the way we're going to use it right now, you can think of it like switch case. CodeSinger 001, the opcode is 6 bits, but it's not just that. Yeah, of course. There's the other parts of the op that actually determine what it is, or yeah. There's the various parameters and stuff. Hey, and I did convert it to Big Endian already. Oh man, Endianness is so fun with emulators. So I may dig into that byte Endian crate sooner than I wanted to, or the byte order crate sooner than I wanted to, but I just really want to run this one op, and I'm gonna be so happy when we do. What am I looking for? I'm looking for the opcodes. So let's go back to our user's manual for this, and we want the CPU instruction set summary. Now we actually know what instruction this is going to be because we have disassembled this. We know it's going to be an LUI, but what I want to do is I want to break down the instruction into these different parts and then double check that what we get matches what this says. Yeah. So what I want to do now is I want to go into our this, and I want to actually look up LUI. And we found right here, load upper immediate. So I thought that might be unsigned immediate. Looks like it's upper immediate. So it shifts the 16-bit immediate 16 bits to the left, clears the lower order 16 bits of the word to 0, stores the result in RT by sign extending the result in 64-bit mode. So TJS off to bed. Good luck in getting the op to run. Yeah, thanks a lot again for your help. Hopefully see you next time. Good night. So this is almost really, really simple because I'm not entirely sure if we're going to sign extend or not because I wasn't sure if we were in the 64-bit mode. I'm going to assume we are just to do this, and then we're going to see if this is wrong or not. So load up immediate. Unfortunately, this didn't have the opcode. There it is. Yeah, okay, so here's, like, I guess the page for the actual instruction set details. See if I can make this smaller. Nope, can't. Gonna deal with it. Okay, so we're trying to check for these lower 6 bits. So we're gonna match the opcode to 0B001111. And it's that syntax. We're gonna run the op. And here's what I want to do. This is what I want to do. We're going to check if it's an opcode we know, and if it is, we're going to do that opcode. Otherwise, we're going to panic on an unrecognized opcode. And so if we get this, we know our decoding's wrong. And I think what CodeSinger said is probably correct, that I probably did decode this wrong because I already shifted everything to Big Endian. So this is probably the wrong way to do this. But I want to try it first. We'll see what happens. Because I actually feel like it's going to be okay. Anyway, we'll see. I want to print this out, actually, just to make sure we got it. We got LUI. And just from there, let's see what happens. 267. Yeah, I need to put a scope around this. Oops. Oh, whoops, because I did logical AND. All right, we got LUI, so I guess we did decode it correctly. And this is just going to keep happening because I never actually increased the program counter. I better do that. After we run the opcode, which we'll do in a second. Codeslinger 001, maybe it's okay since it's within the span of a byte. I think it's okay because I read these in backwards. Like I read these in as if I were reading in a big endian value, but my system, my host CPU is little endian, and because of the way I shifted these, I think I loaded them into the right bytes. So I think this is correct given the fact that my host CPU is little endian. So I think that's why that works. In answer to Codeslinger's question. Yeah, so we got LUI, and then we're going to run our opcode. After we run the opcode, we are going to do self.regpc plus equals 4, which is the size of our word. Cool, so we got an LUI, and then we got 0x10. Again, if we look at our thing, right, the opcode was 0x10, so I don't want to print the opcode here. I want to print the op word. Op word, just so we see the whole thing. 40896000, and that's exactly what this is. Cool, so we're reading these correctly. Now we want to actually interpret this opcode. So we're going to go back to our data sheet. 16-bit immediate, so we need to get that op, or that immediate value. So let immediate value, I'll just say M in this case, is going to be the op word. It's going to be the lower 16 bits, so and 0xFFFF. That's the whole thing. And so then what we do, that's just the regular part. Output is instruction, of course. Lol. Great. Silly me. So let's do this. Now we have our immediate part, and we also, there's going to be these 5 bits of just nothing. And then there's going to be the target register, which is these 5 bits. So let's target is, actually we'll say RT, so that matches the data sheet. We'll be shifting left by 16 bits. Codeslinger said I'll have to shift the immediate left by 16 bits. I want to leave this one unshifted because that's the immediate part, and I want that to correspond to this. When I put it in the register, that's when I'm going to do the shift. So RT is going to be this part, and so that's going to be instruction shift right 16 to move those bits out of the way, and it was 5 bits, so we'll do 1, 2, 3, 4, 5. So now we have the immediate and target parts of the opcode. Now we actually need to put it in there. So one of the things, again, that I found confusing is, this is actually a really nice notation here. I want to go over this really quick. This is saying the operation in 32-bit mode, it will be the general purpose register indexed by the RT value is going to get the value of the immediate value or 0 to the 16th. And I'm guessing you would assume that this, you wouldn't need the shift because I guess this OR is just saying like there's 16 bits of this and then there's this. Not necessarily a binary OR where you put the values together. And then this is saying the same thing for 64-bit except that we get the sign extend component here, which is taking the 15th bit of the immediate value and doing 32 of those. Now again, I'm not entirely sure if we're in 32 or 64-bit mode on startup, and I'm a bit confused about that. So I'll write a little to-do, check 32 versus 64-bit mode for sign extend. I'll also do this, LUI, because we're going to remove this print in a sec. And what I want to do then is actually do that operation. So I'm just going to assume, oops, did I say 13? 32. Currently 32-bit mode is assumed, which is probably wrong, but let's do it for the sake of getting this done. So now we're going to do self.gpr, and there is going to be a certain case. So what I'm actually going to do is write GPR. I'm going to make this a function. Self.writeGPR, and we're going to give the index and the value. In this case, it's going to be immediate shift left 16. Cool. So now if we implement this write GPR instruction, or function, that down here, function write GPR, we're going to have the index. I'll make that a U size because it's going to be indexing into that array. We can cast it there. Ashimadai. Good morning, Ferris Stream Stuff. Nice to see it started. Good morning. Good to see you. The index, and then we're going to do the value, which is going to be U64 because the general purpose registers are 64-bit. And then we're just going to do self. Oh, whoops! We need mutable reference to our self. Self.gpr indexed with index is value. And the reason why I made this a function and didn't inline that is because we do have a special case. If we remember from yesterday, the first general purpose register will always have the value 0. So what I actually want to do is if index is not 0, then we'll do this. That's why I made that a function. And that's pretty sick. So, okay, so I want to do one more thing now. I want to also make a public function to run a single op. And I'll tell you one in a second. Run single op, we'll call it that for now. And we'll actually take all of this code here. Actually, we'll just call this run instruction. And we'll, yeah, rename run instruction. The reason why I want to do this, tab all this back out, is that I want to, in our top level code, in main, I want to just run one instruction. And we'll have to bubble that up through the N64, but that'll be okay. So we're doing it, yeah, we're doing it for testing because I want to print the state before and after. So I want to, we'll remove this print here. Actually, we'll leave it, not a big deal. Just to get this looking good. We don't want to print that whole state, actually. Okay, we'll figure that out in a sec. What exactly we want to print, but we do want this to still run that one instruction. So this all looks good. And let's just, for the sake of debugging, make a print regs thing here. Actually, I don't think the Rust pretty print stuff will actually print all that data. I think it'll just print some of the array. I say we actually just go for it. Move away says at some point you want to be able to debug yourself, and yeah, I will. Let's see if we can get away with not doing that though. Yep, and we'll do reference to N64. Before and after printing. That'll be fine enough. Stick debug back on all this stuff. I did want this pretty printed. And let's do that. Now the compiler will tell us everything else we need to do. 61 in CPU. Yeah, I forgot a mute self in run instruction. And again, this needs self here. It's funny because I haven't been writing C++ in a while, but I guess I've been reading a lot of it. Self GPR, yeah, because it's reg GPR, isn't it? So we'll change the name of this function as well. We call that reg GPR, not just GPR, so that we understand it's a register. Yeah, so this immediate value that we wrote to there, we also need to cast the right type. Fine by me as U64. Debug is not implemented for N64. Also, no method named N64. Yeah, because we need to bubble that run instruction method up to the N64, which we'll probably have a different interface for when this is more production ready. But for now, let's stick with it. Yeah, we'll just do that here. Of fun run instruction and mute self. Self.cpu.run instruction. And we'll do that debug thing here while we're at it. Derive debug, so we'll be able to print this thing. Sorry if I'm going a bit fast at this point. I just am so excited about getting this ready. Yeah, so go back into CPU because write reg, this call here needed to cast RT as a U size. Debug is not implemented for CP0. That makes sense. We're going to need to add it to all these as well. Here. And CP0. Oh, yeah, it has default, but it doesn't have debug. Interconnect doesn't have debug. So go to interconnect and we'll stick that on there. Debug is not on the type reg config. Oops. Setting CPU. Which we already have open underneath, but that's okay. Yeah, because did it all the way except for this struct here. And why did that loop? Oh, it was actually probably printing all that data. Oh, that's funny. Okay, so we're going to actually implement debug ourselves for the interconnect so that we don't have to print the whole RAM. I'll just do that here. Impl debug for interconnect. Now, if I remember correctly, the signature for this was kind of not the prettiest thing. That's actually not that bad. I'm going to actually qualify it like this because we're going to need to pull that in. So this is going to have function format. Don't need self to be mutable. We're going to take in a formatter. And we're going to return a format result. And the nice thing about this is if you can look at the example here, it just shows us we can use this write macro with the formatter. And I'm just going to write to do here. And not worry about that. We'll be okay. So yeah, so now, because I didn't import format, oops, dash, which it shows me to do here, it complained about not knowing what FMT : stuff was. That's fine. Now we have not all control paths return a value. Right, because we didn't return a result. I believe that macro will just return the result. Yes, it will. So we just remove the semicolon, and that should do it. Move Away and Codeslinger are on top of their game. All right, so I think we got it. So we had the before state has all these general purpose registers as 0 in a particular PC. We are also going to want to implement debug for the CPU so that we can print this as hex. For now, we'll not worry about it. Actually, does it work to just put the hash in there and then we'll get that? We'll get all value. Oh no, because we did that anyway. So not going to worry about it. So this was the before state, and then we got LUI, and then we have the after state where this one particular register, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the ninth register, had a value in it. Welcome back, kittens. So that ninth register had a value in it. If we go back here, this should tell us that was T1. So I believe we read the wrong register. Not a problem. Let's go and look at the decoding again. So this started at bit 16. It was 5 bits long. But it could be that I misread the endianness of the target register. Because 5 bits and one of them would have been set. No, because that would have been way higher for that number. Man, we are so close, you guys, to having our first instruction actually more or less properly implemented. Let's get back out of here. Oh, close there. CPU instruction formats. RT, 5-bit target register number or branch condition. And it doesn't appear to tell us the endingness of that value. It could be that I also maybe accidentally read an extra bit. So let's look at this. And guys, 11 o'clock, we're going hard today. Opcode is the instruction. No, okay, we were looking at RT. So it's the instruction shift right 16 bits because that's when it started, and we took 5 bits, which should be correct if it were 5-bit. Let's look at LUI again. Maybe this says something here. Doesn't look like we get much here. Let's look back at LUI, see if we missed something. Move Away says should be shift 15, right? I don't think so, because I think the immediate value was 16 bits. I think that would be correct if it were 15 bits. But it started at bit 0. 0 through 15 to, you know what? I think you're right. I think it is shift right 15. Or Zorg also thinks it was 16, so now I'm second guessing myself. Because I do feel right about that actually, because this is bits 0 through 15, which is a total of 16 bits, and if we wanted to move all of them out of the way, we would have shifted right that many bits. So I do think that is 16. So something else is happening here. Very interesting. So we have 16 to 20. Let's go ahead and print this. RT. It does say RT was 9. I want to look at the opcode again. Okay, so this definitely reads 9 here, if that were an 8-bit value. And if it were just the 5 bits there, that would still be 9. And 9 is the first and last bits? No. I was not thinking correctly there. 9 would have been the 8-bit and the 1-bit. So these instructions operate on T0, which says 08. So I wonder if maybe there's an encoding here about like T and S. So here we have S is down here, and those look to be zeros. So let's look at the register list. Again. CPU registers. It could also be that just R and T is a way of specifying source and target, and you just write those anyway. So those might be insignificant. Yeah, so kitten's about the different number of bits we have. This has 6 here because we're separating the top 6 bits of the instruction word, and this is trying to separate the 5 bits that represents the RT part of that, because they're different parts of the same word. So that's correct, which numbers of bits we have here. But somehow we're still wrong. Somehow 09 here makes sense, and I don't know why. Let's look at LUI again. Let's look at the instruction set overview. Data formats and addressing. It might be. No, I'm thinking, never mind. I was thinking maybe that the target also, with that last bit, maybe that's encoding 32 or 64 bit mode. That might be a guess. Because it's definitely... Also, CPU uses byte addressing for half-word word and double-word access with the following alignment constraints, so I guess you can only do these accesses on full words. Again, not what we're looking for, but interesting. So, CPU instruction formats again. I'm actually just gonna Google MIPS instruction encoding, and just see if we get anything helpful that might be easier to read than the datasheet. So here we say encoding MIPS instructions. Here's an instruction format where we have RT. Whoa, Seabiscuit. Oh, this is, I guess it's saying, yeah, the opcode map. I want to see, search for RT. I don't think that was the most helpful. I just manually decoded it and got 4 for RT, says Zorg666. So I find that a bit strange because if we look back at our disassembled one, it does say T1, and I really want to believe that that's the first general purpose register. Like, the part of me really wants this value to be 1. But see, there's also 32 general purpose registers, so it would make sense that we would use the 5 bits to encode that address, actually. So 5 bits should be the correct amount. And it is 9, but why? Why does this say T1, but this is 09? Yeah, RS should be 0 for LUI. Yeah, when we looked at the at this here and we searched for LUI, I'll show you that again. It did say here, like, yeah, this is where the source would be, and it does say 5 zeros. So that should be zeroed out if this was correct. And then we have the 6 bits here for the opcode itself, which we have correctly read. We have the immediate value, which is the lower 16 bits, and then we have these 5 bits that are left. And man, when I look at that disassembly, this 09 should be correct. Like, 09 is definitely those 5 bits. Because it's going to be the 1 bit, not the 2 bit, not the 4 bit, but the 8 bit. It's going to be 01001, which is 9. So why does 9 mean T1? Maybe there's something there. Let's search MIPS register names. Let's see if that helps. Alternate register names in MIPS. So T0, T1 through T9 are temporary registers. When you make a subroutine call, the callee does not have to say these registers if it wants to use these registers. However, the caller wants to use temporary registers after JL call. Okay, actually, guys, I think we're onto something here. Yeah, okay, right here. Chart of corresponding registers. Name T0 through T7 starts at 8 through 15. So 09 is totally correct for the index register we're using. It just happens to be called T0 because it's one of the designated temp registers. So what this means is that we've totally emulated our first instruction correctly. I'm just gonna wait for that to catch up with the stream delay. Ooh, 00, ugh. Yep. But now we know this for sure, and we've understood this correctly. And that's actually pretty cool. So the next instruction is an MTC0. And I know that that communicates with the C0 coprocessor, as TJ has told us yesterday. So what this looks like it's going to do is it's going to move T1's value into register 12 of the C0. CodeSinger001, so do you have to push that onto the stack then? No, I think what this is telling us is just that these are like the general purpose registers are indexed, and so they're numbered 0 through 31. And I think these are just like alternate names for those indexes. Move away 0 says cool, more like confusing and unnecessary. Probably, but I think this would make sense if you were writing assembler for this. It would be nice to sort of, have certain indices sort of designated as things that you normally use. And I don't know. I think this kind of makes sense. It did definitely confuse us because it didn't seem to be mentioned anywhere, but we did eventually find it. Zorg, oh gosh, I can't believe I forgot that. I took a class where we learned MIPS last year. Yep. Okay. So here's what I think, guys. I think this is really cool. We have successfully emulated our first instruction. And of course, we might be a little bit wrong versus in regards to the 32 versus 64-bit mode. But we've been at this now for 4 hours. And we finally made it, and I think this is really cool. And I think this is going to be a good point to stop. And the next time we do this, we'll start going over the MTC0 and start implementing, more of this stuff. I also want to look at the byte order stuff and implement that more properly, and just start cleaning stuff up. But yeah, I think now is a good time to stop. At least I know that I'm done with this for today. So I'm going to do a really quick commit. We ran our first instruction. So that's pushed. Ashmadai, you're storing VODs, right? Need to catch up later since I'm going to work now. Yes, I am uploading all this to YouTube. So this will be up. I'll probably upload this tonight. Now that I have all that stuff set up. And I'm going to go find all the links that we looked at too and post those in the GitHub as well. Codeslinger, thanks Ferris. Awesome session. Thank you guys for staying along with me. It's been long, but I also think this is pretty cool. Kittens, even though it took a long time, this is really interesting. Glad you think so. Really appreciate it. The Strange Enigma, thanks for streaming this. Super interesting stuff. Again, thank you guys for coming along. Zorg666, awesome progress. Ashmadai, he's uploading to YouTube. Yes. So before I go, last time I just answered a few questions. So if you guys have any more questions, fire away. Ashmadai, yeah, Daniel Cullen, he has totally been watching these. Ryan Hebert, thanks. Looking forward to the next one. Awesome. Hope to see you there. Codeslinger's 001. How many hamsters can fit in the glove compartment of a 57 Chevy? At the risk of saying something pretty morbid, it depends on how much you can stuff them in there. Is that Mackay Fire? How long until the recording is posted? Tuned in late. It'll probably be a couple hours because these I just dump these exactly as they are onto YouTube, and so it can probably take a few hours for this to upload. I'll probably leave it overnight, but it'll just be public, and then tomorrow I'll probably like spam it on Reddit and stuff. Kittens, what's your favorite color? Used to be green, now it's probably black. Ashmadai, thanks man. Catch you later. Off to work. Have fun at work. Thanks for joining us. Codeslinger 001, 57 Chevys didn't have glove compartments. I love it. Move away, but correct. Awesome. Just gonna wait a minute in case there are any other questions that roll in. Yeah, it looks like that's it. So yeah, thanks again, guys. This has been really fun. I'll upload this as soon as possible, and I'll also, like I said earlier, find a lot of these links to stuff that we found and post those on GitHub so we can actually get some of this documentation in one place. So thank you all very much, and I guess I'll see you next time. Bye-bye.